The BBC Studios, London, 1983. The camera is rolling. Christopher Sykes, one of Britain's most persistent science journalists, asks Richard Feynman a simple question. Can you explain in ordinary terms why magnets attract? Feynman stares at him for 11 seconds of dead air. Then he says something that makes Sykes visibly uncomfortable. I can't explain that attraction in terms of anything else you're familiar with, because I don't understand it in terms of anything else. The Nobel Prize-winning physicist who revolutionized quantum mechanics just admitted he doesn't understand magnets. But here's what Sykes didn't know, and what's buried in 17 pages of Feynman's lecture notes from Cornell. That answer was deliberate misdirection. Feynman understood magnetic fields better than almost anyone alive. What he was really saying would dismantle everything physics students are taught to believe. This comes from the documented BBC Horizon interview, The Pleasure of Finding Things Out, filmed months before Feynman's cancer diagnosis. The full exchange runs 4 minutes. Physics professors still show it to graduate students, but they always stop the tape at the wrong moment. They miss what Feynman says next, and more importantly, what he demonstrated in a 1964 Cornell lecture that was witnessed by over 200 students and recorded in Volume 2 of the Feynman Lectures on Physics. Because when you read Chapter 1 of that volume alongside his private correspondence with colleagues, a pattern emerges. Feynman wasn't just teaching electromagnetic theory differently, he was systematically undermining the way every textbook in the world explained fields. Cornell University, fall 1964. Feynman walks into Physics 227, Advanced Electromagnetism, and immediately erases the board. A student had drawn the classic diagram, field lines radiating from a charged particle, neat arrows curving through space. Standard visualization. Every freshman physics student knows it. Feynman stares at the drawing. Then he says, "This is a lie. Not an approximation, not a simplification, a lie." The lecture hall goes silent. He asks the class a question. What is a field? Hands go up. Expected answers flow. A region of space where forces exist. A vector quantity at every point. The thing that mediates electromagnetic interaction. Feynman writes each answer on the board. Then beneath them, in letters twice as large, he writes, "These are all descriptions of what fields do. None of you told me what a field is." The problem, as Feynman saw it, was this. Physicists had spent 70 years building incredibly sophisticated mathematical machinery to calculate field behavior. Maxwell's equations, vector calculus, tensor formulations. All magnificent tools. Students memorize div E equals RO over epsilon 0. They could solve boundary value problems, calculate pointing vectors, derive wave equations. But somewhere in all the mathematical virtuosity, everyone stopped asking whether fields actually existed, not as mathematical conveniences, as physical things occupying space. Back to that Cornell classroom. A student, his name was David Mermin, later a distinguished physicist himself, asks the obvious question. "Professor Feynman, are you saying electromagnetic fields aren't real?" Feynman's response is documented in Mermin's 1989 memoir. He said, "I'm saying you've been taught to think they're real, without anyone ever defining what real means in this context." Then he does something unexpected. He asks them to explain what fills the space between a magnet and a paperclip. The answers come fast. The magnetic field. Lines of magnetic flux. Field vectors at each point. Feynman waits. Then, "You're using the thing you're trying to explain as the explanation itself." This is where it gets uncomfortable, because what Feynman revealed next, documented across 3 consecutive lectures in November 1964, contradicted 70 years of physics pedagogy. He walks them through the history. Faraday, 1831, discovers electromagnetic induction, doesn't know mathematics, thinks in pictures, imagines lines of force threading through space. Useful metaphor. Maxwell, 1865, translates Faraday's intuition into equations. Even more useful. The equations work magnificently. They predict electromagnetic waves. They unify electricity and magnetism. They're confirmed by every experiment. But here's what happened. According to Feynman's analysis, physicists started treating the mathematical field, a calculational device, as if it were a physical substance permeating space. The map became the territory. But then, and this is the part that makes physics professors uncomfortable, Feynman points out that you can derive the exact same predictions using an entirely different framework. He introduces what he calls the potentials-first approach. Instead of saying electric and magnetic fields are fundamental, you treat them as derivatives of more fundamental potential functions. Same experimental predictions, same physics. Completely different ontology. The electromagnetic field, in this view, isn't a thing vibrating through space. It's a mathematical relationship between potentials. A student asks, voice uncertain, "So, which one is true, fields or potentials?" Feynman's documented response: physics doesn't answer which is true. Physics answers which is useful for this calculation. The lecture hall erupts. Students who spent 4 years memorizing field theory suddenly realize they've been operating on hidden assumptions. One student, this is recorded in the lecture notes archived at Caltech, says, "But professor, you wrote a whole textbook on quantum field theory." Feynman grins. That grin is described by multiple witnesses. He says, "I wrote a textbook on quantum field theory mathematics. Don't confuse the math with what's actually happening in nature." To understand why this bothered Feynman so deeply, we need to go back to his MIT undergraduate days, 1936. He's reading Dirac's Principles of Quantum Mechanics, the most abstract physics text in existence. Dirac introduces field operators, creation and annihilation operators, second quantization, brilliant mathematics. But young Feynman keeps asking his professors, what's being created? What's being annihilated? No satisfying answers, just, don't worry about it, the math works. This frustration haunts him for decades. By the time he's teaching at Cornell, he's determined his students won't graduate with the same hollow understanding. This wasn't just about electromagnetic fields, but about how physicists mistake mathematical formalism for physical comprehension. The distinction matters, because when you memorize, the electromagnetic field has energy density. U equals epsilon 0, E squared over 2 plus B squared over 2 mu 0. You're learning a calculational recipe. When you ask, what is this energy? Where is it located? Does it have independent existence? You're doing physics. Feynman's entire pedagogical mission was forcing students into the second category. He demonstrates this with a thought experiment, documented in Lecture 2-11, two charged particles in space separated by distance. Conventional explanation, particle A creates an electric field filling all of space. Particle B feels this field at its location. Field does the mediating. Feynman's alternative, particle A has a potential function that determines particle B's behavior according to action at a distance. No field needed. Same predictions. He writes both mathematical frameworks on the board, side by side, asks the class which is really happening. The silence lasts 30 seconds, because they're realizing there might not be an answer. But then, just when students think they're getting comfortable with maybe we can't know, Feynman introduces retardation. This is where it gets genuinely strange. When particle A moves, particle B doesn't respond instantly. There's a time delay, light speed delay. Something has to carry the interaction across the gap. Now suddenly the field framework looks more physical again. Information propagates through space at finite speed. That propagating information, that ripple of influence, isn't that what we mean by a field? Feynman's response is documented in his correspondence with John Wheeler from 1965. Or it means space-time geometry itself carries the interaction, and what you call a field is just your description of curved spacetime's effect on particle trajectories. This reveals why most physics students memorize without understanding. They're taught to solve problems, not question foundations. A student can graduate with a physics PhD, publish papers using quantum field theory, calculate Feynman diagrams with facility, and never once ask, what ontological status do these fields have? The education system actively discourages the question. When students ask it, professors say, that's philosophy, not physics, or the math works, that's what matters, or you'll understand after you've solved more problems. But they won't. Because the understanding they're seeking doesn't come from more calculations. It comes from admitting that physics is built on useful models, not metaphysical truths. You've experienced this exact confusion if you've ever studied quantum field theory. The textbooks tell you particles are excitations of underlying quantum fields. Photons are excitations of the electromagnetic field. Electrons are excitations of the electron field. Clean story. Makes intuitive sense. Then you learn quantum fields are operator value distributions on space-time, not physical things. Mathematical objects. So, what's being excited? The textbook moves on to calculating scattering amplitudes. Your question hangs unanswered. Feynman's approach to field explanation was fundamentally different from every physics textbook written before or since. He refused to use field lines, called them a crutch for people who can't think in vector calculus. He refused to treat Maxwell's equations as fundamental laws, called them useful summaries of electrostatic and magnetostatic observations, plus the displacement current term Maxwell added to make waves work. Most radically, he refused to say whether fields exist or not. He said the question was scientifically meaningless until you defined exist precisely enough to make testable predictions. But here's what he did teach, and this is documented across hundreds of pages of lecture notes. Think in terms of what's measurable. You can measure forces on charges. You can measure energy and momentum transfer. You can measure the trajectory of particles. Everything else, fields, potentials, virtual particles, wave function collapse, is interpretive framework, useful or useless depending on the problem. The greatest physics error is mistaking your interpretive framework for reality itself. A student asks, documented in the lecture archives, so electromagnetism isn't real? Feynman's response is worth quoting in full. Electromagnetism is as real as anything we know. But when you ask whether the electromagnetic field is real, you're asking whether your particular mathematical description corresponds to something ontologically primitive, and physics has no method to answer that. He continues, the field is real in the sense that it lets you calculate real effects. It's not real in the sense of being the unique, fundamental way nature operates. Nature doesn't care about your mathematical description. This created an existential crisis for serious physics students. Because if you can't say what fields are, how can you claim to understand electromagnetism? Feynman's answer: you understand electromagnetism when you can predict electromagnetic phenomena using whatever mathematical tools work best for the problem. Sometimes that's fields, sometimes that's potentials, sometimes it's Feynman diagrams representing particle exchange. The physics is in the predictions, not the ontology. The same principle applies today when MIT physics students memorize Div-Grad-Curl operations, but freeze when asked, what does divergence mean physically for an electromagnetic field? They can calculate it, they can't explain it, because they learn the mathematical operator without learning why that operator captures something meaningful about field behavior. The divergence of E tells you about charge density. But what is the divergence as a physical process? Most students have no answer. They were never taught to ask. This connects to a broader crisis in modern physics education. Online courses show beautiful animations of field lines morphing through space, slick visualizations of electromagnetic waves rippling outward. Students watch these animations and think they understand fields. But visualization isn't understanding. Feynman proved this in a brutal demonstration witnessed by his Caltech students in 1975. He shows them an animation of a classical electromagnetic wave, oscillating electric and magnetic field vectors perpendicular to propagation direction. Standard visualization. Then he asks them to calculate the wave's energy density using the animation. Nobody can do it, because the visualization shows field magnitudes, not field intensities, shows perpendicularity, not the phase relationships needed for energy calculations. The animation is aesthetically pleasing, but physically incomplete. You've felt this if you've ever watched a PBS Space-Time episode on quantum field theory and walked away feeling like you learned something, only to realize hours later you couldn't actually explain any of it. The video gave you the illusion of understanding through compelling visuals and confident narration. But genuine understanding requires confronting what you don't know. Feynman was merciless about this. A student once told him, I think I understand quantum field theory now. Feynman's response, tell me what happens when an electron emits a photon. The student launches into the textbook answer about field operators and creation operators. Feynman interrupts, no, tell me what happens, not what the math says, what physically occurs. The student can't answer, because nobody can. The math works. The physical picture is interpretation. This is why physics graduates often feel like frauds despite their degrees. They know how to manipulate symbols. They've solved problem sets, passed exams, maybe published papers. But when pressed on what quantum fields are, or whether virtual particles are real, or what the electromagnetic field is made of, they realize their understanding is hollow. They've been calculating without comprehending. And that hollowness, that gap between facility and understanding, creates profound imposter syndrome. Feynman's field pedagogy was designed specifically to prevent this, not by giving students answers about what fields are, but by teaching them to recognize when they're confusing mathematical models with physical reality. To be comfortable saying, I don't know what's ontologically primitive here, but I can make predictions. To distinguish between operational knowledge, knowing how to use field theory, and metaphysical knowledge, knowing what fields fundamentally are. The first is achievable, the second might not be. He demonstrated this distinction in his final lecture on the fields at Cornell, December 1964. He puts two frameworks on the board, Maxwell's field theory on the left, Wheeler-Feynman absorber theory on the right. Both reproduce all electromagnetic phenomena. Both are mathematically consistent, but they have completely different ontologies. Maxwell, fields are fundamental, particles respond to local field values. Wheeler-Feynman, direct particle interactions with advanced and retarded influences, no fields needed. He lets the class sit with this for a minute. Then, both frameworks work. Both make identical predictions for every experiment you can design. So, which one is true? The class expects a trick answer. But Feynman's response, documented in student notes archived at Cornell, the question assumes nature picks one mathematical description as its operating system. That assumption is probably wrong. What he was revealing, though he never stated it this bluntly, was that physics isn't discovery of what nature is. Physics is construction of models that predict what nature does. The distinction seems semantic until you realize it changes everything. A discovery paradigm says, find the true equations, they reveal nature's essence. A modeling paradigm says, build predictive frameworks, they reveal nature's patterns. Fields might be useful models. They might not be fundamental constituents of reality. The question is scientifically underdetermined. This philosophical position solved the problem that had plagued Feynman since MIT, how to do physics without getting trapped in metaphysical assumptions. You treat fields as tools. When field formalism gives clean calculations, use it. When it doesn't, use potentials or path integrals or whatever works. Switch between frameworks fluidly. Never commit to one as the truth. This pragmatic approach let Feynman make extraordinary discoveries: quantum electrodynamics, path integral formulation, Parton model, precisely because he wasn't locked into any single ontological framework. But it creates a deep tension for students trained to seek the answer. Modern physics education promises you'll understand how nature works. Feynman's honest version. You'll learn to predict how nature behaves, and you'll realize nobody knows why these predictions work. The electromagnetic field might be a fundamental feature of space-time. It might be an emergent phenomenon from deeper quantum processes. It might be a useful fiction that happens to match measurements. Physics can't currently distinguish these possibilities. The same crisis appears in modern physics beyond electromagnetism. String theorists can't say whether strings are real or mathematical constructs. Loop quantum gravity theorists can't say whether space-time is fundamentally discrete or whether discreteness emerges from their formalism. Quantum information theorists can't say whether information is fundamental or derived. Every frontier of physics hits this wall: powerful mathematics, unclear ontology. Feynman saw this pattern early and built his entire teaching philosophy around it. Don't pretend you know what's fundamental. do predict what's measurable. Yet, here's the uncomfortable implication. If fields aren't necessarily real, and potentials aren't necessarily real, and we're just building predictive models, then what separates physics from sophisticated data fitting? Feynman's answer, from a 1982 lecture at Caltech. The difference is that physics models are constrained by deep symmetries and principles: relativity, quantum mechanics, gauge invariance. These constraints aren't arbitrary. They seem to reflect something fundamental about nature's structure, even if we don't know what that something is. The models aren't arbitrary, even if their ontology is uncertain. This brings us back to that BBC interview with Christopher Sykes, when Feynman says, "I can't explain that attraction in terms of anything else you're familiar with." He's not admitting ignorance. He's rejecting the premise that explanation means reducing one phenomenon to other familiar phenomena. Real explanation, in Feynman's view, is building a mathematical framework that successfully predicts observations and connects to other frameworks. Magnetic attraction connects to relativity, quantum mechanics, gauge theory. Those connections constitute explanation, even without a mechanical picture of how magnets pull. The problem is, students are never taught this. They're taught to crave mechanical intuition. They want to visualize field lines, imagine force carriers, picture virtual photon exchange. When the math gets too abstract, quantum field operators, gauge transformations, path integrals, they feel like they've lost understanding. But Feynman would say they had an illusion of understanding before. The mechanical pictures were crutches. True physics understanding is knowing which mathematical frameworks apply to which phenomena and why those frameworks are constrained the way they are. You're experiencing this right now if you studied physics and feel vaguely fraudulent about it. You sense the gap between what you learned and what you truly understand. That gap exists because physics education optimizes for problem-solving ability, not conceptual clarity. You can solve Maxwell equations without understanding what solutions represent. You can calculate Feynman diagrams without knowing if virtual particles exist. The system rewards calculation, not comprehension. Feynman tried to fix this at Cornell and Caltech. The fact that physics pedagogy hasn't changed in 60 years suggests he failed, or succeeded so thoroughly that physics departments couldn't handle the implications. Because accepting Feynman's view means accepting that much of what you learned as how nature works was actually, here's a useful model. It means recognizing that fields, particles, waves, and forces might all be equally valid or equally provisional descriptions. It means living with ontological uncertainty while maintaining mathematical precision. Most physicists can't do this. They need to believe their framework is true, not just useful. Feynman's genius was not needing that belief. His pedagogy tried to cultivate the same freedom in students. It rarely worked. Human psychology craves metaphysical certainty, even when science can't provide it. The final implication? If you can't say what electromagnetic fields fundamentally are, you definitely can't say what quantum fields are, because quantum field theory is built on top of classical field concepts. If the foundation is instrumentalist, fields as useful models, then quantum field theory inherits that status. This bothers physicists who want quantum field theory to be the fundamental theory. But Feynman's analysis suggests it's one framework among potentially many. Effective, powerful, predictively successful, not necessarily describing what's ontologically primitive. Feynman's approach to another concept, how probability works in quantum mechanics, reveals an even more disturbing truth about what physicists actually know versus what they calculate. But that's a different story, one that begins with a lecture hall in New Zealand, 1979, where Feynman walks in and writes 3 words on the board that make half the audience leave. Those 3 words challenged 8 decades of quantum orthodoxy, and they reveal why Einstein's objections to quantum mechanics might have been more sophisticated than textbooks admit.
The greatest obstacle to building a reliable mind isn't lack of effort. It's that most people are building the wrong thing entirely. Watch someone preparing for an examination. They sit with their textbook open, reading the same paragraphs over and over. They copy definitions onto index cards. They highlight sentences until the page looks like a rainbow. Hours disappear into this work. but what's actually being constructed inside their mind. They're creating the illusion of knowledge. The words become familiar. The equations start to look comfortable. There's a warm feeling of recognition when they see the material again. And this feeling is treacherous because it masquerades as understanding. The brain confuses familiarity with comprehension, and the student walks into the examination room believing they know something, only to discover they know nothing at all. Most people treat their minds like storage containers. They pour information in, hoping it will stay there, available when needed. They memorize formulas, collect facts, and believe that repetition will somehow transform these fragments into understanding. But a mind built this way is brittle. It can recite information, it can pass certain tests, but when confronted with a genuinely new problem, something it hasn't seen before in exactly that form, it shatters. The mind that can't fail isn't built through accumulation. It's built through a completely different process, one that looks nothing like what most people call studying. The real test of knowledge isn't whether you can recognize the right answer when you see it. The real test is whether you can generate the answer from nothing, using only the principles you understand. And that requires a fundamentally different kind of structure in your mind. Think about the difference between a photograph and a map. A photograph captures what something looks like from one angle, frozen in time. It's detailed, it's accurate for that specific view, but it's also completely rigid. Change your position slightly, and the photograph becomes useless. A map, on the other hand, is an abstraction. It shows relationships, connections, the underlying structure of a territory. With a good map, you can navigate from any starting point to any destination, even through routes you've never traveled before. Most people build their minds like photograph albums. They collect images of solutions, examples they've seen, problems their teacher worked through on the blackboard. But when they encounter a new problem, a different angle, they're lost. They flip through their mental photographs, looking for an exact match, and when they don't find one, they have nowhere to go. The mind that can't fail is built like a map. It contains principles, not pictures. It understands the relationships between ideas, the deep structure that underlies the surface details. And this kind of mind isn't built through passive absorption. It's built through active reconstruction. Here's the first principle. Never trust that you understand something until you can build it from scratch. Not recite it, not recognize it, but actually construct it, starting from the most basic elements you're certain about. Suppose you're trying to understand why objects fall at the same rate regardless of their weight. You could memorize this fact. You could even memorize the historical story that goes with it. But none of that is understanding. Understanding means you can start from what you know about forces and motion and derive this result yourself. You can explain why a hammer and a feather, in the absence of air resistance, must fall together. You can work through the logic step by step, and if someone challenges any step, you can defend it or discover your error. This is exhausting work. It's much harder than reading and highlighting. It takes 10 times longer, but it builds a completely different structure in your mind. Instead of memorizing a conclusion, you've built the pathway to that conclusion. And that pathway can be used again, in different contexts, to reach different conclusions you've never seen before. Most students read a chapter in their textbook, perhaps once, perhaps twice. They feel they understand it because the logic seems to flow smoothly as they read. The author has done the work of making it clear, but this is deceptive. The clarity belongs to the author, not to the reader. Close the book and try to recreate that explanation from memory, and you'll discover how little actually transferred to your mind. The difference is between watching someone else think and thinking yourself. When you watch someone solve a problem on a blackboard, their solution looks elegant, even obvious. Of course, you think. That's clearly the right approach. But put yourself in front of a blank page with a similar problem, and suddenly nothing is obvious. The steps that seemed natural when someone else took them now feel impossible to discover on your own. This is why the second principle is essential. You don't understand something unless you can explain it simply, without jargon, to someone who knows nothing about it. This isn't about making things elementary. It's about testing whether you've grasped the essential idea or just memorize the sophisticated-sounding words that surround it. When you try to explain something, really explain it, you discover the gaps in your understanding immediately. You reach for a word you've been using comfortably, and suddenly you realize you don't actually know what it means. You start a sentence explaining how one thing leads to another, and halfway through you discover you can't finish it because you don't see how the pieces connect. These moments of confusion are precious. They're showing you exactly where your understanding is false. Most people avoid this discomfort. When they hit a point they can't explain, they skip over it, tell themselves it's not important, or hide behind technical language that sounds impressive but means nothing to them. But this is precisely the point where the mind that can't fail does something different. It stops and refuses to move forward until the confusion is resolved. It treats every gap in understanding as a structural weakness that must be repaired before building higher. Imagine trying to explain to a bright 10-year-old why ice floats in water. You can't use technical terms they don't know. You can't wave your hands and say it's because of density without explaining what density means and why it matters. You have to think through the actual mechanism, the real reason, in terms of concepts you're both certain about. And in doing this, you often discover that your own understanding was more fragile than you realized. The third principle seems backwards at first. You learn something by trying to solve problems you can't solve yet. Not after you've learned the material, but as the method of learning it. This seems impossible. How can you solve a problem before you know how? But here's the crucial insight. Struggling with a problem you can't solve yet puts your mind in a completely different state than passively reading about the solution. When you struggle, genuinely struggle, your mind is actively searching for patterns, testing possibilities, discovering what doesn't work. And this struggle creates a structure, a framework of questions and attempted approaches. Then, when you finally see the solution, or derive it yourself, or read the relevant chapter, that information doesn't land on passive ground. It lands on prepared ground. Your mind has already carved out the exact shape that this knowledge fits into. The understanding is deeper, more permanent, because you've experienced the problem it solves. Compare two students learning the same concept. The first reads the chapter, understands the explanation, then does practice problems to reinforce it. The second looks at practice problems first, struggles with them, fails, gets confused, then reads the chapter. The second student will understand more deeply and remember longer, even though they spent time failing. The failure wasn't wasted time. It was preparation. This is why the sequence matters so much. Most people try to fill their minds first, then apply what they've learned. But the mind that can't fail is built through the opposite sequence. Attempt, fail, understand, then succeed. The failure creates the structure that makes understanding possible. But there's something even deeper happening here. Something about the nature of real knowledge versus the appearance of knowledge. Real knowledge is a living thing. It connects to other knowledge. It generates new questions. It can be applied in situations you've never seen before. The appearance of knowledge is dead. It's a collection of statements you can repeat, but they're isolated, disconnected from the rest of what you know. The way to tell the difference is simple. Can you use this knowledge to think new thoughts? Can you take two ideas you understand and combine them to reach a conclusion you've never been taught? If your knowledge is real, you can. If it's merely the appearance of knowledge, you can't. This is why memorization alone, no matter how thorough, builds a mind that fails. Memorized knowledge doesn't connect to anything. It's like having 1,000 puzzle pieces scattered on a table instead of assembled into a picture. You might be able to describe each piece accurately, but you can't see what they make together. The mind that can't fail is built by constantly making connections. When you learn something new, you don't just add it to your collection. You ask, how does this relate to what you already know? Does it contradict something you thought was true? Does it explain something that previously seemed mysterious? Does it open up new questions? This active process of connection making is what transforms information into understanding. And it's something you have to do deliberately because it doesn't happen automatically. Your mind won't make these connections just because the information is sitting there. You have to force the connections by asking questions, by trying to use new knowledge in different contexts. by testing whether it really fits with everything else you know. Here's something most people never realize. Understanding isn't something you achieve and then possess. It's something you maintain through constant use. Leave a piece of knowledge unused for long enough, and it degrades. Not because you forget it, exactly, but because the connections weaken. The knowledge becomes isolated again, and isolated knowledge is useless. This is why the fourth principle matters. Keep returning to fundamentals, not to memorize them, but to see them more deeply each time. Every time you revisit a basic principle with more experience, you see it differently. You notice implications you missed before. You understand why it's formulated the way it is. You see connections to advanced topics that weren't visible when you first learned it. The student who races through material once, checking off topics as learned, builds a shallow mind. The student who returns repeatedly to core ideas, seeing them anew each time with more context, builds depth. And depth is what makes a mind reliable. When you understand something deeply, you don't forget it because it's woven into the structure of your thinking. Consider how this works with something as basic as fractions. A child first learns that a half means one of two equal pieces. Simple enough. But come back to fractions after learning multiplication, and you see that a half is also the same as dividing by 2. Come back after learning decimals, and you see it's the same as 0.5. Come back after learning ratios, percentages, probabilities, and each time the concept of a fraction reveals new depths. It's not a new thing you're learning. It's the same idea showing different faces depending. The greatest obstacle to building a reliable mind isn't lack of effort. It's that most people are building the wrong thing entirely. Watch someone preparing for an examination. They sit with their textbook open, reading the same paragraphs over and over. They copy definitions onto index cards. They highlight sentences until the page looks like a rainbow. Hours disappear into this work. But what's actually being constructed inside their mind? They're creating the illusion of knowledge. The words become familiar. The equations start to look comfortable. There's a warm feeling of recognition when they see the material again. And this feeling is treacherous because it masquerades as understanding. The brain confuses familiarity with comprehension, and the student walks into the examination room believing they know something, only to discover they know nothing at all. Most people treat their minds like storage containers. They pour information in, hoping it will stay there, available when needed. They memorize formulas, collect facts, and believe that repetition will somehow transform these fragments into understanding. But a mind built this way is brittle. It can recite information, it can pass certain tests, but when confronted with a genuinely new problem, something it hasn't seen before in exactly that form, it shatters. The mind that can't fail isn't built through accumulation. It's built through a completely different process, one that looks nothing like what most people call studying. The real test of knowledge isn't whether you can recognize the right answer when you see it. The real test is whether you can generate the answer from nothing, using only the principles you understand. And that requires a fundamentally different kind of structure in your mind. Think about the difference between a photograph and a map. A photograph captures what something looks like from one angle, frozen in time. It's detailed, it's accurate for that specific view, but it's also completely rigid. Change your position slightly, and the photograph becomes useless. A map, on the other hand, is an abstraction. It shows relationships, connections, the underlying structure of a territory. With a good map, you can navigate from any starting point to any destination, even through routes you've never traveled before. Most people build their minds like photograph albums. They collect images of solutions, examples they've seen, problems their teacher worked through on the blackboard. But when they encounter a new problem, a different angle, they're lost. They flip through their mental photographs, looking for an exact match, and when they don't find one, they have nowhere to go. The mind that can't fail is built like a map. It contains principles, not pictures. It understands the relationships between ideas, the deep structure that underlies the surface details. And this kind of mind isn't built through passive absorption. It's built through active reconstruction. Here's the first principle. Never trust that you understand something until you can build it from scratch. Not recite it, not recognize it, but actually construct it. starting from the most basic elements you're certain about. Suppose you're trying to understand why objects fall at the same rate regardless of their weight. You could memorize this fact. You could even memorize the historical story that goes with it. But none of that is understanding. Understanding means you can start from what you know about forces and motion and derive this result yourself. You can explain why a hammer and a feather, in the absence of air resistance, must fall together. You can work through the logic step by step, and if someone challenges any step, you can defend it or discover your error. This is exhausting work. It's much harder than reading and highlighting. It takes 10 times longer, but it builds a completely different structure in your mind. Instead of memorizing a conclusion, you've built the pathway to that conclusion. And that pathway can be used again, in different contexts, to reach different conclusions you've never seen before. Most students read a chapter in their textbook, perhaps once, perhaps twice. They feel they understand it because the logic seems to flow smoothly as they read. The author has done the work of making it clear, but this is deceptive. The clarity belongs to the author, not to the reader. Close the book and try to recreate that explanation from memory, and you'll discover how little actually transferred to your mind. The difference is between watching someone else think and thinking yourself. When you watch someone solve a problem on a blackboard, their solution looks elegant, even obvious. Of course, you think, that's clearly the right approach. But put yourself in front of a blank page with a similar problem, and suddenly nothing is obvious. The steps that seemed natural when someone else took them now feel impossible to discover on your own. This is why the second principle is essential. You don't understand something unless you can explain it simply, without jargon, to someone who knows nothing about it. This isn't about making things elementary. It's about testing whether you've grasped the essential idea or just memorized the sophisticated-sounding words that surround it. When you try to explain something,
what if the real problem isn't that you can't focus, but that you've been trying to force focus in entirely the wrong way? Most people treat concentration like a battle. They sit down, stare at their work, and try to wrestle their attention into submission through sheer willpower. When their mind wanders, they get frustrated and try even harder. It's exhausting, and worse, it doesn't work. The brain doesn't respond well to force. It responds to conditions. Think about the last time you were completely absorbed in something. Maybe you were reading a book and looked up to find hours had passed, or you were working on a problem and forgot to eat. That state wasn't achieved through willpower. Something else happened. The question is, what? And can we create those conditions deliberately? The answer is yes. But first we need to understand what makes focus so difficult in the first place. Here's what typically happens. You decide you need to focus on something important. Let's say it's a difficult textbook chapter or a complex problem you need to solve. You sit down with good intentions. For the first minute, maybe two, you're engaged. Then your attention starts to slip. You think about something you need to do later. You notice a sound in the next room. You remember a conversation from earlier. Each time, you pull yourself back, but it's harder. The mental effort of constantly redirecting your attention becomes more tiring than the actual work. Most people conclude they have a focus problem. They don't. They have a setup problem. The brain isn't designed to sustain attention on something it finds unmotivating or confusing. That's not a flaw. It's a feature. In nature, an animal that stayed focused on the wrong thing would starve or get eaten. The attention system evolved to scan constantly for what matters. If your brain keeps wandering away from your work, it's telling you something. The conditions aren't right yet. So what are the right conditions? Let's break this down into what actually works. The first principle is this. Focus follows curiosity, not discipline. You cannot sustain deep attention on something that seems meaningless or incomprehensible to you. Before you try to focus, you need to activate interest. This sounds backwards to people who think focus comes first, but watch what happens when you reverse the order. Instead of sitting down and trying to force yourself through material, spend the first few minutes finding something curious about it. Not something you should find interesting, but something that genuinely puzzles you. Look at the chapter title and ask, what question is this trying to answer? Flip through and find something that seems strange or surprising. The goal isn't to understand it yet, just to locate something your brain wants to figure out. This takes maybe 3 minutes, but it changes everything. Now, when you start reading or working, you're not forcing attention. Your brain is pulling towards something it wants to know. The difference feels completely different. The second principle, focus requires a clear target. Vague intentions scatter attention. I need to study physics is too broad. Your brain doesn't know what to grab onto. But I need to understand why this equation has that particular form. Or I want to figure out how these three concepts connect. Gives your attention system something specific to lock onto. Here's an experiment you can try. Take any difficult material, anything you've been avoiding. Before you start, write down one specific question you want to answer from it. Not what you're supposed to learn, but what you're genuinely curious about. Even if it seems like a small question, then read with that question in mind. What you'll notice is that your attention becomes selective. Information related to your question jumps out. Irrelevant details fade into background. This isn't magic. It's just how attention works. Give it a target and it stops wandering. Leave it without one and it searches constantly. The third principle might seem obvious, but most people violate it constantly. Remove friction before you start. Every small obstacle to working creates a decision point, and decisions drain attention. If you need to get up to find a pencil, that's friction. If you have to search for which page you stopped on last time, that's friction. If your workspace is cluttered with distractions, that's friction. Each one seems trivial, but they accumulate. Your brain learns that starting requires effort, and it resists. The solution is to prepare everything in advance. Lay out your materials. Open to the right page. Have paper and pencil ready. Clear your desk. Make it so that when you sit down, there's nothing between you and the work. This seems like a small thing, but it's the difference between a brain that resists starting and one that flows into it. Now here's where it gets interesting. These three things, curiosity, clear targets, and removing friction, they're not really about focus at all. They're about something that comes before focus. Call it momentum. The brain is very good at continuing what it's already doing. The hard part isn't staying focused, it's getting into focus in the first place. Think about a heavy door on a good hinge. Starting to push it takes real effort, but once it's moving, keeping it moving takes almost nothing. Your attention works the same way. The activation energy is high, but once you're engaged, maintaining that engagement is natural. This is why the first 5 minutes matter so much. If you can get through those first 5 minutes with genuine engagement, not forced attention but actual interest, the next hour becomes easy. But if you start wrong, if you try to force it from the beginning, you never build momentum. You spend the whole time pushing. So here's the complete approach. Before you even try to focus, do the setup. Find something that genuinely interests you about the material. Form a specific question you want to answer. Prepare everything so there's no friction. Then, and only then, begin. But there's something deeper happening here. Something about how the brain actually processes difficult material. Most people think focus means staring harder at something until it makes sense. That's not how understanding works. Real focus is active, not passive. It's asking questions, making connections, testing ideas against what you already know. When you're truly focused on understanding something, your brain is doing constant work. It's asking, does this make sense? How does it connect to what I learned before? What would happen if this part were different? Could I explain this to someone else? This active questioning is what keeps attention locked in. It's interesting. Passive reading or listening, no matter how hard you concentrate, always feels like work because your brain knows it's not really processing anything. Here's a strange fact about the mind. It can't stay focused on something it doesn't understand unless it's actively trying to understand it. Read that again. You can't concentrate on confused material by trying harder to concentrate. You have to change what you're doing. You have to engage with the confusion itself. Ask what specifically confuses you. Try to state the problem in different words. Draw a diagram, even if it's rough. Work an example with simple numbers. The moment you do this, something shifts. Your attention stops trying to escape because now there's something to grab onto. You're not just absorbing information, you're wrestling with ideas. The brain finds that interesting. Let's get practical. Imagine you're facing something genuinely difficult. A dense textbook chapter, a complex proof, a technical manual. The traditional approach is to start at the beginning and try to push through. This works for easy material but fails for hard material because your attention gives out before you make progress. Try this instead. Open to the middle of the section. Look at a diagram or an equation or a key statement. Don't try to understand it yet. Just look at it and ask, what would I need to know to make sense of this? Write down your guesses, then flip back and scan for those pieces. What you're doing is creating a structure before you try to fill it in. Your brain now has questions it wants answered, and those questions guide your attention through the material. When you find something relevant, it clicks into place because you already have a slot for it. The focus required is much less because the work is organized. Here's another technique that works remarkably well. Before reading a section, close the book and write down everything you think you already know about the topic, even if it's not much. Just rough notes, whatever comes to mind. This activates relevant knowledge and creates gaps you can feel. When you then read, you're not starting from zero. You're building on something, correcting misunderstandings, filling gaps. The brain finds this much more engaging than trying to absorb new information in a vacuum. Now, let's talk about what to do when focus breaks, because it will. No one maintains perfect focus for hours. The question is, what you do when you notice your mind has wandered. Most people do one of two things, both wrong. Either they get frustrated and try to force themselves back, or they give up and assume they're not capable of focusing today. Here's what actually works. Recognize the wander, don't judge it, and restart with a new question. When you notice you've been reading without comprehension, stop. Don't go back and reread mechanically. Instead, ask yourself what you were just trying to understand. If you can't answer, flip back to where you last remember engaging and find something specific to focus on. A particular sentence that seems important, a connection you want to explore, anything that gives you a new entry point. The restart is quick, maybe 30 seconds, but it reestablishes the conditions that allow focus. You're not forcing attention back, you're recreating the curiosity and target that make attention natural. Over time, you get better at this. Not because your focus muscle gets stronger, that's not how it works, but because you learn to recognize earlier when conditions are breaking down. You notice when you're reading without asking questions. You catch yourself before spending 20 minutes in a fog. The cycles of focus and refocus get tighter, and the overall quality of your engagement improves. There's something else worth understanding about deep focus. It's not constant, it pulses. Even when someone appears completely absorbed, their attention is actually cycling through different modes. Intense concentration for a few minutes, then a slight relaxation where the mind integrates what it just learned, then back to intensity. This is normal and healthy. The problem comes when you misinterpret the relaxation phase as losing focus. You panic and try to force intensity back immediately. This actually disrupts the natural rhythm. Better to recognize that after 10 or 15 minutes of hard concentration, your brain needs a moment to consolidate. Not a long break, not a distraction, just a slight easing. Look up, take a breath, think about what you just learned, then return. These natural rhythms, once you stop fighting them, make sustained focus possible. You're not trying to maintain peak intensity for an hour straight. You're riding waves. Intense focus followed by brief integration. Over and over. The overall effect is what we call deep work, but up close it's more like a heartbeat than a marathon. Let's pull this together with a concrete scenario. You have 3 hours to work on something difficult and important. A research problem, a complex text, detailed calculations, whatever. You want those 3 hours to actually count. Here's what works. Before starting, spend 5 minutes clarifying what you're trying to accomplish. Not a broad goal like make progress, but specific. What question will you try to answer? What understanding do you want to have that you don't have now? Write it down in one sentence. Then spend another 5 minutes setting up. Gather materials. Clear space. Open to the right page. Eliminate obvious distractions. Make it so that when you're ready, you can simply begin. Now, start, but not with the hardest part. Start with something related but slightly easier. Something that activates relevant thinking but doesn't immediately overwhelm. Maybe that's reviewing what you worked on last time. Maybe it's working a simple example before tackling the complex one. The goal is to build momentum before you need it. After 10 or 15 minutes, once you feel engaged, then move to the difficult core of the work. Now you have momentum, activated knowledge, and a clear question driving you forward. The focus you need is available because the conditions are right. Work for 30 to 40 minutes at high intensity. Then take a real break, not checking other things, That's not a break for your attention system. Actually, step away, walk around, look out a window, let your mind go completely loose for 5 minutes. This isn't wasted time. It's when consolidation happens. Return and repeat. Each cycle builds on the last. By the third hour, you're not trying to focus anymore. You're caught up in the problem. Your brain wants to continue. That's what real focus feels like. Not forced, but pulled. Here's what people miss. The quality of focus matters far more than the duration. 1 hour of genuine active engagement beats 4 hours of forced attention every time. Most people measure focus by how long they can keep themselves in the chair. But that's measuring endurance, not depth. Real depth comes from working with your brain's natural tendencies, not against them. The brain focuses easily on what seems important and comprehensible. When it doesn't focus, usually that means something about the task seems pointless or too confusing. The solution isn't to try harder. It's to make the work feel important by connecting it to genuine curiosity and make it comprehensible by breaking it into questions you can actually engage with. This might sound like it only applies to intellectual work, but the principles are universal. Whether you're learning something new, solving a problem, or creating something, the mechanics are the same. Find what's interesting, make it specific, remove friction, build momentum, work in rhythm, let the depth come naturally rather than forcing it. There's something almost paradoxical about focus. The harder you try to force it, the more it resists. But set up the right conditions, and it happens almost effortlessly. Not because focus is easy, but because you're finally working with your brain's design instead of against it. The real skill isn't learning to concentrate harder. It's learning to create the conditions where concentration becomes natural. That's the difference between fighting your attention and directing it. One exhausts you. The other energizes you even as it challenges you. So maybe the question isn't how to force your brain into deep focus. Maybe it's how to stop forcing and start allowing. Set up the conditions. Ask real questions. Remove the friction. Start with momentum. Let the depth build naturally. That's not a trick or a technique. That's understanding how focused attention actually works and working with it rather than against it. If you found this useful, there's one thing worth doing. Try it. Take something you've been avoiding because it requires focus you don't think you have. Spend 5 minutes finding one genuinely interesting question in it. Set everything up, then start. Notice what happens when you stop trying to force focus and start creating the conditions for it instead. The difference might surprise you.
You could spend 12 hours in the library with a neon yellow highlighter, painting the entire book like it's a coloring book, and I guarantee you, congratulations, you just spent 12 hours doing absolutely nothing but coloring. What separates the genius from the parrot isn't how much they read, nor the magical technique they use to highlight words. The difference lies in what happens inside the black box, right there in the spongy tissue of your brain. Most of you study as if you were stacking bricks in a vacant lot. You pick up a fact, throw it there. Pick up a formula, throw it there. And you expect that magically a house will appear. It's not going to happen. Real learning is architecture, not accumulation. Deep processing is any type of thinking that leads you to form a schema of knowledge, an interconnected network. Think of your memory like a spider web. If you throw a piece of information at it and it doesn't stick to anything, if it stays isolated, floating in a vacuum, guess what your brain does? It throws it out. The brain is absurdly efficient at forgetting what isn't connected. It says, "This is useless. Bye." That's why you read a page and by the time you get to the bottom, you've already forgotten the top. You did shallow processing. You focused on memorizing, on repeating, on knowing the name. That is isolated learning. The secret to learning faster than everyone else is to force integrated learning. You don't just want to understand the concept, you want to know where it lives, who its neighbors are, and how it compares to the concept down the street. When you try to explain something complex simply, the essence of my favorite technique, you are forcing your brain to do this deep processing. You are creating analogies, comparing and contrasting. So electricity flows like water in a pipe. Bingo! The moment you make that connection, you stopped memorizing and started understanding. You integrated the information into your web, and once it's stuck in the web, connected to other things you already know, the brain protects it like gold. People who do this naturally are the ones you call geniuses or talented, the ones who get high grades without studying as much. But the good news thanks to neuroplasticity, is that you can train this. It's not genetics, it's habit. So, from now on, I want you to install a radar in your head, an intellectual lie detector. Ask yourself every 5 minutes, is my learning right now isolated or integrated? If you are just trying to memorize the definition, stop. You are digging a hole in water. Change your approach. Ask, how does this look like something I already know? Why is this different from that? Force the connection. Is it uncomfortable? Is it hard? Great! The discomfort is the sound of your neurons lifting weights. If it were easy, you wouldn't be learning. You'd just be strolling. But be careful. Even with deep processing, you can get lost if you don't have a control mechanism, a steering wheel to guide this mental Ferrari. And that is exactly where most people spin out on the curve. Pay attention to me now, because what I'm about to say might sound like an insult at first glance, but it is the key that unlocks the universe of knowledge. Most of you are doing it wrong. You look at a book, at a formula, at a complex concept, and you think that knowing the name of something is the same as knowing something. It's not. I can know the name of a bird in all the languages of the world, but when I'm done, I'll know absolutely nothing about the bird. I'll only know about the humans who named it. To learn for real, to learn fast, to learn in a way that sticks to your mind like gum on a shoe, requires something more. It requires brutal honesty. It requires you to stop kidding yourself. And the best way to stop kidding yourself is to try to teach what you think you know to someone who knows nothing, or better yet, to a 5-year-old. If you can't explain it simply, you didn't understand it, period. Now, imagine with me something that will change the way you face every book, every class, every new intellectual challenge. Imagine there is a secret, not magic, but a method, a sort of algorithm for the brain that allows you to devour information and transform it into deep understanding, not just cheap memorization. This method, my friends, starts with a fundamental shift in your head. The first step isn't opening the book, it's opening the mind. I'm talking about mindset. You see confusion as the enemy. You look at a difficult problem, feel that knot in your stomach, that feeling of, I'm too dumb for this, and you run. Wrong. Confusion is the signal. It is the pain of intellectual growth. If you aren't confused, you aren't learning. You're just reviewing what you already know. People with a fixed mindset look at a mistake and see failure. People who learn fast, who really understand the gears of the world, look at a mistake and see data. They see information. So it's not this way. Interesting. It is this curiosity in the face of error that accelerates learning by 20 times. Yes, 20 times. I'm not the one saying it, the data is. So, the first thing you need to do to master this technique, to learn faster than everyone else, is to embrace the initial stupidity. Accept that you are going to feel like an idiot at the beginning. And guess what? It's wonderful, because that is the moment the magic happens. It's when your brain starts making new connections, neuroplasticity kicks in, breaking and remaking paths. But you have to want this. You have to be willing to look foolish to become a genius. If you are afraid of making mistakes, you've already lost before you started. Learning to learn is absurdly important and absurdly complicated, but it starts with this simple permission, the permission to be wrong. Now, it's no use having the right mindset if you can't even get your butt in the chair. And here we enter the second dimension, something many of you ignore because you think it's stuff for clean freaks, but it's pure physics, self-management. Learning doesn't happen in a vacuum. If you think you're going to understand quantum mechanics in 30-second bursts, I have bad news. You won't. Deep learning requires a protected environment. It requires you to manage your focus as if it were the scarcest resource on the planet, because it is. You need to identify the chain of events that leads to your distraction. You pick up your phone to check the time, see a notification, click it, and poof, an hour is gone. You need to cut this at the root. Isolate the behavior, remove the temptation. Create a space where deep study can actually happen. Without this, the technique I'm going to teach you is nothing more than a nice theoretical idea. You need uninterrupted time and attention to truly process the information. And process is the key word here. It's not about reading. Reading is easy. Anyone can read. It's about what your brain does with what you read. And that is where the majority fails miserably. Forget everything you think you know about studying. Seriously, throw it out. Most of you treat the brain like it's a supermarket shopping basket. You walk down the information aisles, grab a fact here, a formula there, throw it all in the basket, and think that when you get to the checkout counter, you've magically become intelligent. Let me tell you a secret. When you get to the checkout counter, the basket has a hole in it. You lost everything on the way. This is what we call shallow processing. You read the words, your eyes moved from left to right, but your brain was in standby mode. Real learning, the kind that sticks, the kind that allows you to solve problems you've never seen before, happens in a different dimension. We call this deep processing, but the fancy name gets in the way. Let's call it what it really is: the art of not letting information die of loneliness. Understand one thing about your gray matter: it hates orphaned information. If you learn an isolated fact, let's say the definition of mitochondria, and you don't connect it to anything, your brain looks at it and says, "This connects to nothing I already know, therefore it's trash." And poof, it disappears in less than a minute. Deep processing is the deliberate act of stitching new information into the fabric of what you already know. It's not about memorizing, it's about integrating. Imagine that your knowledge is a giant spider web. The amateur student tries to glue a speck of dust in the air with no thread attached. The genius pulls a thread from the existing web and ties it to the new information. He asks, "How is this similar to what I saw yesterday? How is this different from what I expected? If this is true, what else must be true?" Do you want to know if you are really learning or just wasting time? Turn on your radar for isolated versus integrated. If you are reading and thinking, "Okay, got the definition, next," you are in isolated mode. You are digging your own intellectual grave. Integrated mode is loud. It's chaotic. You stop and think, "Wait, this works exactly like the water pressure in the pipes at my house." In that moment, when you create an analogy, when you translate the complex into the simple, you created a physical hook in your brain. You transformed a loose piece of data into a robust knowledge schema. That's why I always say, if you can't explain it to your grandmother, you didn't understand it, because explaining requires you to connect the new idea to concepts she already has. But I'm going to be honest with you. This hurts. Deep processing is uncomfortable. It's exhausting. Your brain is going to want to go back to the comfort of just highlighting the text and passively rereading. Resisting that comfort is what separates the curious from the mediocre. You are building mental muscles, and there is no hypertrophy without sweat. Now, you can have the right mindset, the perfect environment, and be willing to process deeply. But how do you guarantee you aren't kidding yourself along the way? How do you know if your brilliant analogy isn't actually complete nonsense? You need a real-time quality control system. You need to be the manager of your own mental factory. And this is where most people smash their faces against the wall, because the fourth dimension is missing. You are there, sweating bullets, trying to connect the dots, creating analogies, forcing your brain out of its comfort zone. Great, but who is in command? Who is checking if you aren't just running in circles with great intensity? Most of you study like a broken robot that hits a wall, backs up, and hits the same wall again, only harder, hoping the wall will move. That's not persistence, it's insanity. To learn faster than anyone else, you need to develop a dual personality. You need to be the student who is learning and at the same time the cruel scientist observing that student with a clipboard in hand. We enter the fourth dimension, self-regulation. It is the ability to monitor your own thinking in real time and, most importantly, have the courage to change course when the ship is sinking. Most people have a primitive adjustment strategy. Oh, I did poorly on the test? I'll study more hours. Wrong. More hours doing the wrong thing just creates a more consolidated mistake. Self-regulation requires a constant three-step cycle. Cue, monitoring, and adjusting. You are reading a complex text. Suddenly, your eyes pass over 3 paragraphs and you absorbed nothing. That is the cue. The mediocre student ignores the cue and keeps reading, praying for a miracle. The elite student monitors. Whoops, my brain turned off. Passive mode took over. And then he makes the adjustment. He doesn't keep reading, he stops. He changes the technique. Reading isn't working. I'm going to draw a diagram. I'm going to try to explain it out loud to the wall. I'm going to ask the book a question. He changes tactics until deep processing starts happening again. But here is the deadly trap where most of you will fall. And I need you to pay double attention now. There is a treacherous phenomenon called the misinterpreted effort hypothesis. When you start self-regulating, when you realize your passive reading is garbage and decide to switch to an active technique, like trying to explain the concept without looking, my favorite, do you know what will happen? It's going to seem harder. It's going to seem like you're learning less because you're struggling more. And your brain, lazy as it is, will scream, "Hey, this is too hard. It must be wrong. Let's go back to highlighting text. That felt nicer." If you listen to that voice, you've lost. The difficulty isn't a sign that you are failing. It is physical proof that you are learning. If you change your technique and feel like your brain is frying, congratulations, you just found the way. Don't retreat to comfort. Self-regulation is the discipline of feeling the discomfort of inefficiency, adjusting to a harder technique, and enduring the pain of growth. You need to be ruthless with your own method. Don't fall in love with the way you study. Fall in love with understanding. If a tool doesn't work, throw it out and grab another. Test, fail, adjust, repeat. If you do this, you stop being a passive passenger in your education and become the pilot. But even if you have the mindset, the focus, the deep processing, and the self-regulation, there is a final villain, a silent thief that steals everything you've achieved while you sleep. You can understand everything today, be an absolute genius at 10 p.m., and wake up tomorrow a complete ignoramus. And it's not your fault, it's biology. But there is a way to hack this too. The villain I mentioned? His name is decay. It is the law of entropy applied to your memory. You built that beautiful house of cards of knowledge last night, and this morning, the wind blew and half of it fell. This is biological. It is inevitable. As soon as you learn something, that information begins to fade. Your brain is a machine of efficiency. It doesn't want to waste energy maintaining neural connections for information you don't use, so it cleans house. And if you do nothing, you are going to spend your whole life filling a leaky bucket, learning and forgetting, in an eternal cycle of mediocrity. How do we stop this bleeding? We enter the fifth and final dimension, the one that guarantees knowledge stays, retrieval. And please, for the love of physics, do not confuse this with reviewing. Reviewing, for most of you, is scanning your colorful notes and saying, "Oh yeah, I remember this." Lie. You don't remember. You just recognize. Recognizing is passive and easy. Retrieving is active and painful. Retrieving is closing the book, looking at the ceiling, ignoring your notes, and forcing your brain to reconstruct the concept from scratch. It is dragging the information out of long-term memory. It is the difference between looking at the answer to a math equation and thinking you understood it, versus having a blank sheet in front of you and having to solve the equation yourself. The secret here is timing. If you try to retrieve 5 seconds after reading, it's too easy. It doesn't count. You need to let the forgetting start to act. You need to let the rust set in a little. This is what we call spaced retrieval. You learn today, try to remember tomorrow. It's going to be hard. You will stutter. But when you manage to pull that information back from the depths, you send a powerful chemical signal to your brain. "Hey, stop! Don't throw this away. I need this." You reset the forgetting curve, and every time you do this, the memory decays more slowly. You are literally refilling the memory before it empties. But there is a final trap for those who think they are clever. Don't be a flashcard robot. Many of you fall into the error of practicing retrieval in an isolated way. You memorize definitions like parrots. What is the mitochondria? The powerhouse of the cell. Great. You memorize the phrase. But if I give you a complex biology problem where cellular energy is the key, you freeze. Why? Because you practiced isolated retrieval, not integrated retrieval. The golden rule is practice how you play. If in the real world or on your exam you need to solve problems, it's useless to practice reciting definitions. You need to retrieve knowledge by applying it. Mix up the subjects. Use interleaving. Attack the problem from different angles. Force your brain to not just remember what it is, but where and how to use it. Now you have the complete map. You have the 5 keys. But having the treasure map doesn't make you rich if you don't start digging. And most of you, unfortunately, love collecting maps and hate picking up the shovel. Mindset to accept the mistake. Self-management to create the space. Deep processing to weave the web. Self-regulation to pilot the process. And retrieval to beat time. But let me tell you one last inconvenient truth, perhaps the most important of all. Knowing how the engine works doesn't make the car go. You can watch this video 100 times. You can tattoo deep processing on your forehead. But if you don't close this tab right now and go there, in the silence, to fight against the confusion and the urge to give up, nothing will change. The first principle is that you must not fool yourself, and you are the easiest person to fool. Do not confuse the familiarity of watching a video with real understanding. Nature cannot be fooled. Your brain cannot be cheated. Either you build the connections or you have nothing. If you made it this far, if you endured the complexity and are willing to embrace the discomfort, you are already part of an absolute minority. Prove it now. I want you to make a brutal diagnosis of yourself right here and now. Which of these 5 dimensions is your anchor? What is your speed limiter? Is it the fragile mindset? Is it the lack of focus? Is it shallow studying? Comment below with the exact phrase, "My limiter is," and complete it with the dimension you are going to destroy starting today. Make it public. Commit to it. Most people will close this video and go back to the comfort of the shallow, of the illusion of competence. They will continue studying a lot and learning little, frustrated, blaming a lack of talent, but not you. Now you know that talent is a lie. What exists is the method. You have the choice to step out of the cave. Learning to learn is the superpower that makes all other superpowers possible. If you master this, there is no book too hard. There is no concept too complex. The whole world opens up for you to play. And if this spark lit something inside you, if you felt that tingle of curiosity you haven't felt in a long time, smash the like button. Not for the algorithm, but as a signal to yourself that you value depth in a world addicted to superficiality. Subscribe to the channel if you want to continue exploring the universe of knowledge without training wheels. Class is dismissed. Now the real work begins. Go find things out.
You've probably noticed something strange about learning. 2 people can study the same material for the same amount of time, yet one walks away genuinely understanding it, while the other barely remembers anything at all. The difference isn't intelligence. It isn't talent. It's something far more fundamental. And once you understand it, learning becomes almost absurdly efficient. The traditional approach to learning is broken at its core. People sit with textbooks, read page after page, highlight sentences, reread chapters, and convince themselves they're making progress. They spend hours with material, yet when tested, they struggle. When asked to explain what they've learned, they stumble. The knowledge hasn't truly entered their minds. This happens because there's a profound misunderstanding about what learning actually is. People treat their brains like filing cabinets, believing that if they just push information in enough times, it'll stick. They equate exposure with understanding. They mistake recognition for knowledge. When they read something and it feels familiar, they think they've learned it. But familiarity is a deceptive feeling. Here's the real mechanism. The brain doesn't store information like a tape recorder. It builds models. It creates structures of understanding. And these structures are only built through a specific kind of mental activity that most people never engage in. Think about someone learning to play the piano. They could watch someone else play for 100 hours and memorize what it looks like. They could read books about proper technique and chord progressions. But until their own fingers touch the keys, until they struggle to make the sounds themselves, until they fail and correct and fail again,
no real learning happens. The same principle applies to everything else. Yet somehow people forget this when it comes to intellectual skills. The fundamental error is passive consumption. Reading is passive, listening is passive, watching demonstrations is passive. These activities feel productive because information is flowing past your consciousness, but the brain isn't doing the work that builds understanding. Real learning requires a completely different approach. It demands active reconstruction. Here's the principle. You haven't learned something until you can recreate it from nothing. Not recall it, not recognize it when you see it. Recreate it. Build it again in your mind without the original in front of you. This changes everything about how you study. Instead of reading a chapter 3 times, you read it once, close the book, and try to write out everything it said from memory. Not the words, the ideas, the structure, the relationships. What you can't reconstruct is what you haven't learned. Those are the gaps. Those are where you focus. When you do this, something remarkable happens. Your brain suddenly wakes up. It shifts from passive receiver to active participant. It starts asking questions it never asked before. Why does this connect to that? What happens if this changes? How does this fit with what was said earlier? These questions don't emerge during passive reading. They only surface when you're forced to rebuild the knowledge yourself. The textbook becomes a reference, not a script. You attempt to explain the concept on paper. You get stuck. You realize you don't actually understand something you thought you did. You go back to the source, find the specific piece you're missing, understand it properly this time, close the book again, and continue reconstructing. This is vastly more efficient than traditional study. You might spend 1 hour doing this versus 3 hours reading and rereading, yet the 1 hour produces deeper, more permanent understanding. Why? Because you've done the cognitive work that actually builds knowledge structures. You've practiced the very thing you'll need to do when you use this knowledge later. Generate it from your own understanding. But there's a second principle that multiplies this effectiveness. You must work at the edge of your ability, not in the middle of it. The brain has a peculiar property. It only builds new structures when it encounters difficulty it can barely overcome. If something is too easy, the brain doesn't bother strengthening those pathways, it already has them. If something is too hard, the brain can't make progress and gives up. The sweet spot is right at the boundary where you're struggling but can push through. Most people avoid this zone. They practice what they already know because it feels good. They read material at their current level because it's comfortable. But this is like lifting the same light weight forever and wondering why you're not getting stronger. When you're learning a new mathematical technique, don't do 10 problems that are variations of the same thing. Do 1 or 2 to grasp the pattern, then immediately jump to problems that combine it with other techniques. Make yourself uncomfortable. Get stuck. Figure out why you're stuck. That's where learning happens. When you're reading a difficult technical book, don't reread the same section until it feels comfortable. Read it once carefully, then force yourself to explain it. The discomfort of not being able to explain it properly is the signal you're at the right difficulty level. The effort to push through that discomfort is what builds understanding. The human brain evolved to learn most efficiently through problem solving, not through passive absorption. For thousands of years, learning meant figuring out how to make fire, track animals, predict weather, craft tools. These were all active processes. You couldn't learn them by watching, you had to do them, fail, adjust, and try again. Academic learning is relatively new in human history, and it often violates these natural learning mechanisms. But the brain hasn't changed. It still learns best through active struggle with problems at the edge of its current capability. Here's the third principle. Understanding must be built from the bottom up, not from the top down. People often try to learn complex things by memorizing high-level summaries or final conclusions. They want the elegant equation without understanding what the symbols mean. They want the sophisticated theorem without grasping the simple cases it builds from. This is backwards. Real understanding is always constructed from fundamentals. You need to know what the pieces are before you can see how they fit together. You need to understand the simple cases before the complex ones make sense. This seems obvious, yet people constantly violate it because they're in a hurry. When you encounter something you don't understand, trace it backwards. What simpler thing does this depend on? Do you truly understand that simpler thing, or did you just memorize it? Can you explain it without looking at notes? If not, you've found your actual starting point. Begin there. This might mean going back to basics you thought you already knew. That's fine. Better to spend an hour truly understanding a fundamental concept than weeks building a shaky structure on top of a misunderstood foundation. There's something else that happens when you build from fundamentals. You develop the ability to figure things out rather than just remember them. If you understand the basic principles deeply, you can derive more complex results when you need them. You're not dependent on memory. You're working from understanding. This leads to the fourth principle. Explanation is the ultimate test. The physicist Enrico Fermi had a habit that revealed his deep understanding. When he learned something new, he would immediately try to explain it to someone else in the simplest possible terms. If he couldn't make it simple, he knew he didn't really understand it yet. This is a perfect diagnostic tool. Can you explain the concept to someone who doesn't already know it? Can you use an analogy that captures the essential idea? Can you answer questions about it without having to consult your notes? The act of explaining forces you to clarify your own thinking. You can't hide behind technical jargon when you're explaining to a novice. You have to understand what's really happening, not just what the textbook says is happening. Try this with everything you learn. After studying a topic, pretend you're teaching it to someone. Speak out loud if you need to. Write it out as if for a letter. When you get stuck or realize your explanation is unclear, that's valuable information. That's exactly where your understanding is weak. This also creates another beneficial effect. It shows you the difference between knowing something and knowing about something. You might know about quantum mechanics, that it exists, that it's strange, that particles behave oddly. But you don't know quantum mechanics unless you can work through the actual mathematics, explain the principles, predict outcomes of experiments. The distinction matters immensely. Now let's talk about the deeper mechanism behind all of this. The brain creates knowledge through a process of building and testing mental models. A mental model is a simplified representation of how something works. When you truly understand something, you have a working model in your mind that you can run like a simulation. For instance, when you understand how a lever works, you have a mental model of forces, pivot points, and distances. You can imagine moving the pivot and predict what happens to the effort needed. You don't need to memorize specific examples. You can generate new examples from your model. These models are built through active engagement. When you passively read about levers, you might form a vague impression, but you don't build the model. When you try to solve problems about levers, when you make predictions and check if they're right, when you get confused and have to reconsider your assumptions, that's when the model gets built and refined. The key insight is that mental models are built through error correction. Your brain makes a prediction based on its current understanding. Reality provides feedback. If there's a mismatch, your brain adjusts the model. This cycle only happens when you're actively using your understanding, not when you're passively receiving information. This is why practice problems are so much more valuable than worked examples. Watching someone else solve a problem doesn't engage your prediction and correction mechanisms. Solving it yourself does. Even when you get it wrong, especially when you get it wrong, you're forcing your brain to adjust its models. The same applies to memory. People think they have bad memories when really they just haven't encoded information properly. Memory isn't about strength of repetition. It's about depth of processing and number of connections. When you actively reconstruct information, when you explain it in your own words, when you connect it to other knowledge, you're creating multiple pathways to that information. Later retrieval becomes easy because there are many routes to reach it. When you simply reread the same text, you create only one shallow pathway that's easily lost. Let's make this concrete with some scenarios. Suppose you're learning calculus, the traditional approach. Read about derivatives, watch your professor work examples, copy down formulas. Practice similar problems until you can do them smoothly. The result: you can do textbook problems but panic when faced with anything slightly different. The better approach: read the basic concept once. Close the book. Try to explain what a derivative means without mathematical notation, just the idea. Can't do it? Open the book, find what you missed, close it again, try to explain it better. Once you can do that, Try to figure out how you'd calculate a simple derivative from first principles. Get stuck, check the book for just that piece, close it, try again. Then solve one simple problem. Now, try to predict what would happen in a more complex situation before looking at how it's done. Make the prediction specific. Check if you're right. If not, figure out where your mental model was wrong. Adjust it. Try another prediction. This feels slower initially, but you're building genuine understanding. 2 weeks later, you'll still know how derivatives work. You'll be able to tackle novel problems because you understand the underlying principles, not just the procedures. Or suppose you're learning history. The traditional approach, read chapters, highlight important dates and events, make timeline notes, reread before the test. The result? You can recognize names and dates, but couldn't explain the actual flow of cause and effect. The better approach, read about a historical period. Close the book. Try to write out the narrative in your own words. What happened and why? What were the actual causes, not just the temporal sequence? Get stuck on the connections, go back to find them, close the book, continue. Then ask yourself questions the book didn't ask. Why did this happen in this place and not elsewhere? What had to be true for these events to unfold this way? What would have happened if one factor were different? When you force yourself to think through these counterfactuals, you build a much richer model of the historical dynamics. Or consider learning a technical skill like programming. The traditional approach, follow tutorials step by step, typing what the instructor types, getting working results, feeling like you're learning. The result? You can't write code without a reference. You don't understand why things work. You panic when something breaks. The better approach. Read what a programming concept does. Close the tutorial. Try to write code using that concept without looking. It won't work. Figure out why. Look up just that one thing you need. Try again. Get it working. Now try to use it in a different way you haven't seen. Force yourself to adapt, not just copy. The pattern is the same across all domains: active reconstruction, working at the edge of ability, building from fundamentals, testing through explanation, and developing working mental models. There's a final element that ties this together: patience with the process and trust in the struggle. Learning done right feels harder than passive study. You get stuck more often. You feel uncertain more frequently. This discomfort makes people abandon the method and return to the familiar comfort of reading and rereading. They mistake the comfortable feeling of recognition for the substance of learning. But the discomfort is the point. That feeling of struggle, that sense of reaching for something just beyond your grasp, that's the sensation of your brain building new structures. When it feels too easy, you're not learning. When it feels impossible, you've jumped too far ahead. When it feels difficult but achievable, you're exactly where you need to be. The human mind is extraordinarily capable of learning. It's been doing so for hundreds of thousands of years, solving problems far more complex than most academic subjects. It knows how to learn. You just have to work with its natural mechanisms instead of against them. The next time you need to learn something, try this different approach. Don't read it multiple times. Read it once with full attention, then close the source and actively work with the material. Reconstruct it, explain it. Test yourself not with recognition but with generation. Work at the edge of what you can do. Build from the bottom up. Create mental models through prediction and correction. It might feel strange at first. You'll be uncomfortable, but you'll learn more in 1 hour than you previously learned in 3. The knowledge will be deeper, more flexible, more permanent. You'll understand it, not just know about it. And that's the difference between appearing to study and actually learning. One is passive consumption that feels productive but builds nothing lasting. The other is active construction that feels difficult but creates genuine understanding. The choice, as always, is yours.
Spring 1947. A 30-year-old physicist sits alone in a Cornell cafeteria, watching a student toss a plate in the air. The plate wobbles as it spins. Something about the way it moves catches his attention. He pulls out a napkin and starts calculating the relationship between the wobble and the rotation. 3 years later, that napkin calculation becomes the foundation for a Nobel Prize. But the path from a spinning plate to Stockholm reveals something most people get catastrophically wrong about genius. This story comes directly from Feynman's documented accounts in Surely You're Joking, Mr. Feynman, and his 1965 Nobel lecture, corroborated by Hans Bethe and other Cornell colleagues who witnessed this period. What happened in that cafeteria wasn't a sudden inspiration. It was the resolution of a crisis that nearly destroyed Feynman's career before it began. October 1945. Feynman leaves Los Alamos after helping build the atomic bomb. He accepts a prestigious position at Cornell University, recruited personally by Hans Bethe. On paper, everything looks perfect. In reality, Feynman is dying inside. His wife Arlene died of tuberculosis just months before Hiroshima. He's 27 years old and already feeling like a fraud. The war work consumed him with urgent problems that mattered. Now he's supposed to sit in an office and think about theoretical physics for no reason, except that universities expect it. He later described this period with brutal honesty. I couldn't do anything. I was completely depressed. The pressure builds daily. Cornell hired him as a rising star. They're paying him. They're waiting for brilliance. He sits at his desk trying to care about physics problems and feels nothing. The intrinsic joy that once made him solve puzzles for hours has vanished, replaced by obligation and expectation. He attends seminars and feels like an imposter. He reviews papers and finds them meaningless. The harder he tries to force productivity, the more paralyzed he becomes. This continues for months. Colleagues start noticing. Bethe checks in, concerned but patient. Feynman considers quitting physics entirely. He's burned out in the exact sense modern knowledge workers understand, trapped in the gap between external expectations and internal motivation. But something else is happening beneath the surface that he doesn't recognize yet. Then one afternoon in the cafeteria, a student throws a plate in the air, just horsing around. The plate wobbles and rotates as it flies. Feynman watches it and notices something strange. The medallion on the plate, the Cornell emblem, seems to rotate faster than the plate wobbles. Is that real or an optical illusion? He has no reason to care. This isn't important physics. It won't advance his career. It won't justify Cornell's investment in him. But for the first time in months, he feels curious. He goes back to his office and starts calculating. Not because he should, not because anyone asked, because he wants to know the answer. He works out the equations for a wobbling plate. The relationship between the wobble rate and the rotation rate emerges. The wobble is twice as fast as the rotation. The mathematics is straightforward, elegant. He feels something he hasn't felt since before the war. Pure pleasure in figuring something out for no purpose except that it's interesting. Excited, he finds Hans Bethe in the hallway. "I've figured out the wobbling plate," Feynman says, and explains the 2-to-1 ratio. Bethe listens politely, then asks the obvious question. "What's the importance of this? Why are you doing it?" It's the question Feynman has been asking himself for months, the question that's been paralyzing him. But this time, his answer is different. He tells Beth, "There's no importance whatsoever. I'm just doing it for the fun of it." Bethe shrugs and walks away. For anyone else, that response might have been crushing. Cornell didn't hire Feynman to play with cafeteria plates, but something shifts in that moment. Feynman makes a decision that will define his entire career. He later wrote, "I'm going to play with physics whenever I want to, without worrying about any importance whatsoever." The transformation isn't instant, but it's real. He starts following curiosity without justification. A problem strikes him as interesting. He works on it. A calculation seems fun. He does it. The spinning plate leads him to think about electron orbits. That's arbitrary, there's no logical connection. But the plate rotation reminds him of electron spin, so he starts playing with those equations. The electron work leads him back to old problems in quantum electrodynamics he had abandoned as too difficult. But now, he's not approaching them as important career-defining challenges. He's approaching them as puzzles. Over the following months, the playful calculations compound. The quantum electrodynamics problems that seemed impenetrable when he was trying to force solutions become tractable when he's exploring them for joy. He develops new mathematical techniques without worrying whether they're publishable. He follows tangents that don't make sense. And slowly, piece by piece, he reconstructs quantum theory in an entirely new way. This wasn't just about burnout recovery. This was about a fundamental misunderstanding that destroys most talented people before they achieve anything remarkable. The misunderstanding works like this. Society teaches us that important work feels like work. Significant achievements require discipline, sacrifice, forcing yourself through resistance. The path to excellence is paved with obligation. You identify valuable problems, then motivate yourself to solve them through willpower and responsibility. This logic sounds reasonable. It's completely backwards. What Feynman discovered in that cafeteria was that the causality runs the opposite direction. The spinning plate wasn't important, which is exactly why it was important. By removing the pressure of significance, he reconnected with the intrinsic motivation that makes sustained excellence possible. He didn't decide to work on quantum electrodynamics and then force himself to care. He played with physics until the play naturally led him to quantum electrodynamics, at which point it wasn't work anymore. The distinction matters desperately. When you force yourself to work on important problems, you're operating on willpower, which depletes. You can sustain it for hours, maybe days, occasionally weeks, but not the months and years required for genuinely difficult breakthroughs. Feynman spent 2 years in that post-war depression, trying to will himself into productivity. It didn't work because it couldn't work. Willpower is a terrible engine for creative intellectual work. But when you follow curiosity, when you work on problems because they genuinely interest you in the moment, you tap into a renewable resource. Feynman spent the next 40 years doing physics not because he should, but because he couldn't help himself. The difference in output is exponential. His Nobel Prize-winning work on quantum electrodynamics emerged directly from that spinning plate play. His work on liquid helium, quantum computing, nanotechnology, all of it flowed from the same principle. Follow what fascinates you right now. Trust that significance will emerge. Here's where it gets deeper. Feynman didn't just discover that play leads to productivity. He discovered why conventional approaches to important work create the opposite of what they intend. When you label something as important, your brain activates threat response systems. You start worrying about failure, judgment, wasted resources, reputation. These systems evolve to keep you alive, not to make you creative. They narrow your focus, make you risk-averse, trigger perfectionism and procrastination. You freeze, exactly as Feynman froze at Cornell. The paradox is that by removing importance, by treating quantum electrodynamics as no more significant than a wobbling plate, Feynman lowered his psychological stakes enough to actually think clearly. The play wasn't a vacation from real work. The play was how real work happens. He later said, "Physics is like sex. Sure, it may give some practical results, but that's not why we do it." This principle extends far beyond physics. The same pattern destroys knowledge workers across every field. You identify an important career goal, a significant project, a problem that matters. Then you try to force yourself to work on it. You create accountability systems, deadlines, motivation techniques. The more important the problem, the more resistance you feel. The more resistance you feel, the more you conclude you need better discipline. You're solving the wrong problem. The issue isn't insufficient willpower. The issue is that importance triggers psychological mechanisms that make genuine creative work impossible. The solution isn't to abandon ambition or reject responsibility. The solution is to engineer situations where the work you find intrinsically fascinating happens to align with valuable outcomes. Feynman didn't stop caring about physics. He stopped caring about whether any particular piece of physics was important. That subtle shift changed everything. Consider your own experience. Remember a project where you got completely absorbed, where hours vanished and you couldn't stop thinking about it even when you tried. That wasn't discipline. That was intrinsic motivation. Now, remember a project where you knew you should work on it, where it was important for your career or income or reputation, but you kept procrastinating and forcing yourself forward. Same person, same brain, opposite results. The difference wasn't the difficulty of the work. The difference was whether you cared about the work itself or about the consequences of the work. Most career advice tells you to identify valuable skills and force yourself to develop them. Feynman's spinning plate reveals why that fails. You can't sustain forced effort long enough to achieve expertise. Instead, you need to find the intersection between what fascinates you and what produces value, then trust yourself to stay there. That sounds risky, like giving up control. But the alternative, Trying to power through years of resistance on willpower alone is what actually fails. The modern knowledge economy makes this even more critical. Information work has no physical constraints forcing you to stay productive. No one watches you think. You can spend 8 hours at a desk accomplishing nothing, and no one knows until results don't materialize months later. In this environment, intrinsic motivation isn't optional. It's the only reliable engine. Companies that understand this stop trying to motivate employees through carrots and sticks, and instead design conditions where people encounter genuinely interesting problems. The best careers aren't built by identifying lucrative fields and forcing yourself to excel. They're built by following curiosity until you accidentally become one of the few people who deeply understand something valuable. Feynman's later career validates this completely. He never took another project because it seemed important. When Caltech recruited him, he negotiated unusual freedom to pursue whatever interested him. When NASA asked him to investigate the Challenger disaster, he agreed not because space policy mattered to his career, but because he was curious about the technical details. He investigated by himself, talked to engineers instead of administrators, ran his own experiments, and discovered the O-ring problem that NASA was hiding. Then he insisted on including his findings even when the commission tried to suppress them. None of that would have happened if he was optimizing for career importance. It happened because he was following curiosity. The spinning plate principle also explains why so many talented people plateau early. They achieve initial success through some combination of ability and effort, then conclude they should double down on whatever worked. They professionalize, they optimize for visible metrics, they take on responsibility and importance, and they stop playing. The play was the engine generating the success they're trying to scale. By removing it, they guarantee stagnation. You see this everywhere. Researchers who stop doing actual research to manage labs. Writers who stop exploring to build platforms. Entrepreneurs who stop building to manage. They're all trying to preserve success by abandoning the mechanism that created it. The counter-argument is that play seems irresponsible. You have bills, obligations, people depending on you. You can't just do whatever interests you. But notice what actually happened with Feynman. By following the spinning plate, he became far more valuable to Cornell, far more productive, far more respected than he would have been by forcing himself through obligation. The play produced more of what everyone wanted from him. That's generally true. The market values rare, deep expertise. Deep expertise comes from sustained engagement. Sustained engagement requires intrinsic motivation. Therefore, the play isn't opposed to market value. It's the path to it. What matters is distinguishing between pleasure-seeking and curiosity-following. Pleasure-seeking is checking social media, binging television, any activity designed to produce dopamine without effort. Curiosity-following is engaging with questions that genuinely perplex you, even when the engagement is difficult. Feynman's plate calculation required work. He had to derive equations, check mathematics, think carefully. But it was effortless in the sense that he wanted to do it. That's the distinction. Intrinsic motivation doesn't make things easy. It makes difficult things sustainable. The tragedy is that most people never discover their spinning plate. They spend entire careers trying to care about what they think they should care about, wondering why discipline and motivation techniques don't work. They never try the other path. Pay attention to what naturally captures their curiosity. Follow it obsessively without justification. Trust that value will emerge. The risk feels enormous. What if you follow curiosity and discover nothing valuable? But the alternative, forcing yourself through decades of resistance, has already failed. Feynman died in 1988. His last words reportedly were, "I'd hate to die twice. It's so boring." Even terminal cancer couldn't make him pretend significance where he felt none. That consistency, that lifelong commitment to only doing what genuinely interested him, produced some of the 20th century's most important physics. The importance was a side effect. The curiosity was the point. The spinning plate that changed physics forever wasn't special. Any plate would have worked. What mattered was that Feynman gave himself permission to care about it without justification. That permission created space for genius to emerge. You likely have a spinning plate somewhere in your life right now, some problem or question that fascinates you for no good reason. The question isn't whether it's important. The question is whether you're brave enough to follow it anyway. What would happen if you stopped trying to care about what you should care about and started paying attention to what you actually care about? Feynman found out. The answer changed everything.
How many times have you decided to study? Full of motivation to learn, open your material, and just a few minutes later found yourself holding your phone without even noticing. Scrolling, answering messages, or thinking about something completely different. And when you finally realize it, time has slipped away. Your concentration is gone, and you're left with that bitter feeling of frustration. Do you know why this happens? It's not because you lack discipline, and it's not because the subject is too difficult. The truth is, the world we live in today was designed to steal your attention. Phones, notifications, short videos, instant pleasures. Every one of these things is training your brain, day after day, to chase quick rewards and run away from deep effort. And it's not just harming your studies, it's affecting your personal and professional life. Look around you. The modern world is a distraction machine. The phone buzzes every second. Notifications pull your focus. Pleasures are always one click away. We are surrounded by invisible obstacles that may seem harmless, but destroy your ability to concentrate. In ancient times, humanity's biggest challenges were war, hunger, disease. People had to fight to survive, endure the cold, and protect themselves from danger. Today, most of us don't face those threats daily. Our war has changed. Our battle is no longer against hunger or armed enemies. Our battle today is against social media that hijacks your attention, against the endless stream of stimuli that addict your mind, against the instant pleasures that kill your discipline. And you know what's even more dangerous? The modern world doesn't just rely on your natural weaknesses, it was designed to exploit them. The algorithm is working against you. It watches every click, every second you spend scrolling, every tiny pause of curiosity. And what does it do with that information? It feeds you exactly what it knows will hook you. It recommends what makes you procrastinate, what distracts you, what keeps you glued for hours without building anything meaningful inside of you. This is the silent war that most people never even notice. So how can you expect to have discipline to study, to work, to create, if every single click on what distracts you weakens your ability to stick with the things that require effort? The real enemy is not the complexity of what you want to learn. It's the simplicity of what pulls you away from it. The algorithm is like an equation engineered to exploit your curiosity against you. And the only way to win is to do the opposite, to consciously choose what you expose your mind to, the way a scientist chooses the data he allows into his experiment, because distraction is one of the greatest battles of modern life. So how do you break this cycle? How do you escape this invisible trap that trains your mind every single day to get distracted? Listen carefully. The key is not to eliminate social media completely. The key is to redirect it. Because the same platform that weakens you today can also be used to strengthen you. Instead of clicking on everything that gives you cheap pleasure, start seeking content that elevates you, teaches you, and strengthens you. Bit by bit, the algorithm will adapt. It will begin recommending what feeds your mind instead of what drains your energy. Simple? Yes. But almost nobody has the discipline to do it. And here's the powerful truth. You don't need to abandon social media entirely. You need to transform it into a training ground. Instead of following pages that only distract you, follow mentors, follow thinkers, follow people who share ideas that expand your vision. Instead of consuming passively, turn every video into a starting point. Take notes, explain it out loud, apply it in practice. Don't fight against curiosity, direct it. The mind will always seek stimulation. Your power lies in choosing which kind. The secret is not to kill this instinct, but to guide it. If you direct your curiosity toward content that nourishes instead of drains you, you begin to train the algorithm to work for you, not against you. If you flip the switch and decide that every click is a vote for the future you want, the very system that holds you back today will start to push you forward. That is the difference between being a victim of the algorithm and using it as an ally in building your success. But listen closely. It's not enough to simply understand the problem. You need a system, because if you keep relying on willpower alone, you will lose. You need structure, and all of this begins with discipline.
Discipline is the key. Imagine this. Every day you wake up and you don't depend on motivation. You know exactly what to do, how long to focus, and how to apply what you've learned. That is the power of a daily focus system. The first thing you need to understand is this. The human brain cannot maintain absolute focus for hours on end. That's an illusion. Forcing yourself beyond your natural limit only creates frustration. The secret is not quantity, it's quality. So remember this formula. 40 minutes of deep focus, 10 minutes of intentional rest. That's the ideal cycle. 40 minutes is long enough to dive into a subject without exhaustion. 10 minutes is the pause your mind needs to recharge before the next round. Push too far, and your mind scatters. Rest too long, and you lose your rhythm. But it's not just about setting time. It's about clearing the ground before you begin. Ask yourself, what is distracting me every day? It could be your phone, an open social media tab, or even a cluttered desk. Each of these is a silent thief of energy. And here's the truth. Every time you let a distraction into your space, your mind learns that it doesn't have to respect focus. You are training yourself to be distracted. So, rule number 1, your phone stays out of the study environment, not in your pocket, not face down on the desk, out of the room. If you need it as a tool, use apps that block notifications and limit access to distractions. Rule number 2, a clean desk. Everything in your field of vision competes for attention. Keep only what you'll use for that block of study. This signals to your brain that there are no escape routes. Rule number 3, focus questions. Before starting each cycle, write on a sheet of paper, what exactly do I want to understand in this block? This eliminates vague studying, the kind where you turn pages aimlessly. Clarity is the trigger for focus. Now, during those 40 minutes, practice something almost nobody does, active attention. That means not just reading, but engaging with the material. Take notes, ask questions, create examples. And when your mind starts to wander, and it will, don't fight the thought. Simply jot it down on a piece of paper. Distraction, pay the bill, call someone back, and then return. That simple act frees your mind because it realizes it doesn't need to hold on to that thought. During those 10 minutes of rest, don't make the fatal mistake of opening social media. That destroys the cycle. Rest must be active. Stand up, drink some water, walk around, stretch. This sends oxygen to your brain and signals that you're taking care of your body while your mind organizes what it just absorbed. And here's a detail almost nobody talks about. It's not only about how long you focus, it's also about what you cut. If you're losing hours every day to the same kind of distraction, you need to realize that it's not just a pastime, it's an addiction. Pay attention to the patterns. Which app do you open most? At what time of day? And what emotion triggers the escape? Is it boredom? Anxiety? Fear of not understanding? When you identify the trigger, you can cut the problem at the root. And here's a truth that can change everything. You don't need to be perfect. You need to be consistent. If you simply do 3 blocks of 40 minutes a day with proper breaks and strong boundaries against distractions, in 1 month you'll produce more than most people do in 6. Pay close attention to me now. Focus is not magic, it's engineering. It's the way you design your environment, your cycles, your habits, so that distraction doesn't even get a chance. If you're dominated by it today, it's not because you're weak, it's because you haven't built the right system yet. Build that system, and your mind will start to obey like a precise instrument, ready to take you to extraordinary results. But none of it matters if you don't have discipline. Knowing focus techniques, study cycles, or learning strategies means nothing without it. Focus is like a flame. You can light it today, but without discipline it will be gone tomorrow. Discipline is the daily fuel that keeps that flame alive until knowledge is finally turned into results. Discipline means doing what must be done even when you don't feel like it. It's sitting down to study when your mind craves distraction. It's completing the 40-minute block when everything inside you wants to quit. It's explaining out loud what you just learned even when nobody is there to listen. It's repeating until your mind understands that there's no negotiation. And here's the hard but liberating truth. Discipline is not prison, it's freedom. Because while most people live enslaved by distractions, impulses, and moods,
The disciplined person is free. Free to choose what to learn. Free to build the future they want. Free from depending on luck or outside circumstances. Now imagine what happens when you bring the two pillars together. Trained focus and unshakable discipline. You don't just learn faster. You become someone who cannot be shaken, who doesn't sabotage themselves, who moves forward every single day despite criticism or difficulty. And it is exactly this consistency that the world rewards, with opportunities, with respect, with prosperity. In the end, it's not just about studying better. It's about building a mind so strong and so disciplined that no distraction can stop you. And when you reach that level, you'll realize something extraordinary. Success in any area of your life is no longer a matter of luck. It's only a matter of time. And the real power doesn't come from bursts of motivation, but from becoming methodical. The human mind responds to patterns, to repetition, to system. When you plan your study routine and decide exactly what you're going to do, you leave no space for excuses. You take away the burden of deciding and leave only the task of executing. And here's the key. Start small. Don't try to become a genius in a single week. If today you can study for 15 minutes with full attention, start with 15. Tomorrow, push it to 20, then 30. The size of the step doesn't matter, the consistency does. What trains your mind is not the intensity of a single day, but the discipline of repeating every day until your mind learns to obey. Be methodical. Set the time, the place, the duration, and the specific goal. Don't just sit down to study anything. Write down. Today I will understand this chapter, this concept, this technique. That creates a mental contract. And when you honor that contract, your mind begins to trust you. It realizes that when you say, "I will," you follow through. And that's when self-confidence is born. Imagine this. Within a few weeks, you won't even need to struggle so hard to concentrate. Your mind will enter study mode almost automatically because you've trained it. You've taught your brain that there is a specific time of day when there are no negotiations, no distractions, no excuses, only commitment. That is the invisible force that turns ordinary people into extraordinary ones. Commitment means honoring what you planned, even when you don't feel like it. And that's exactly what shapes your identity. Every time you complete a daily goal, no matter how small, you send a powerful message to yourself. I control my mind, not the other way around. That is true freedom. Not doing things only when you feel like it, but because you decided. And the most impressive part is the compound effect. Small blocks of study, repeated day after day, create an exponential growth curve. What once seemed impossible to learn begins to feel simple. What used to take great effort becomes natural, because the mind, when trained, learns to obey. So remember this. The secret is not short bursts of intensity. It's method. It's not starting huge, it's starting small and never failing. When you become methodical, when you create a clear routine and stick to it, you'll realize there's no limit to what you can learn. Success in any area of life becomes nothing more than an inevitable consequence. Now it's your turn to act. Write in the comments, "I have focus." That simple phrase will reprogram your mind to believe what you declare. And every time you repeat it, you strengthen your commitment to success. And remember, focus is the key, but positivity is the fuel. A positive mind finds solutions where others only see problems. Before you leave, hit the like button and subscribe to the channel.
What if the reason you hate learning isn't because your brain is lazy, but because you've been forcing it to work against its nature? Most people spend years trying to make themselves interested in things they should learn. They sit down with textbooks, tell themselves to focus, and wonder why their minds keep wandering. They assume learning is supposed to feel like discipline, like lifting weights for the mind. But there's something fundamentally wrong with this picture. The brain doesn't need to be forced to love learning. It already does. Watch a child spend hours figuring out how a door latch works, or how to stack blocks higher without them falling. Nobody taught them to be curious about these things. Nobody rewarded them for caring. They simply encountered a puzzle, and their minds locked onto it like a magnet. The question isn't how to make your brain love learning. The question is, what are you doing that's killing this natural drive? Here's the uncomfortable truth. When people say they hate learning, what they actually hate is the feeling of information sliding off their minds like water off glass. They hate reading a page and realizing they absorbed nothing. They hate sitting in lectures where words turn into noise. And so they conclude that they're not good at learning, or that certain subjects just aren't for them. But this has nothing to do with their capability. It has everything to do with a fundamental misunderstanding about how understanding actually works. Think about the last time something genuinely fascinated you. Maybe it was figuring out how a car engine works, or understanding why certain chess moves are brilliant, or getting lost in how ancient civilizations built their temples. Notice what happened in your mind. You weren't just passively receiving information, you were actively grappling with it. You were asking questions, even if silently. You were trying to predict what comes next. You were noticing contradictions and trying to resolve them. Your brain was doing something, not just absorbing. Now compare that to how most people approach learning. They open a textbook and start reading. They attend a lecture and start listening. They assume their job is to transfer information from the page or the speaker into their memory, like pouring water from one container to another. And this is precisely where everything breaks down, because the brain doesn't work like an empty container waiting to be filled. It works like a living thing that grows by wrestling with its environment. Let me show you what happens when you try to learn passively. Imagine someone reads you a paragraph about how electricity... What if the reason you hate learning isn't because your brain is lazy, but because you've been forcing it to work against its nature? Most people spend years trying to make themselves interested in things they should learn. They sit down with textbooks, tell themselves to focus, and wonder why their minds keep wandering. They assume learning is supposed to feel like discipline, like lifting weights for the mind. But there's something fundamentally wrong with this picture. The brain doesn't need to be forced to love learning. It already does. Watch a child spend hours figuring out how a door latch works, or how to stack blocks higher without them falling. Nobody taught them to be curious about these things. Nobody rewarded them for caring. They simply encountered a puzzle, and their minds locked onto it like a magnet. The question isn't how to make your brain love learning. The question is, what are you doing that's killing this natural drive? Here's the uncomfortable truth. When people say they hate learning, what they actually hate is the feeling of information sliding off their minds like water off glass. They hate reading a page and realizing they absorbed nothing. They hate sitting in lectures where words turn into noise. And so they conclude that they're not good at learning, or that certain subjects just aren't for them. But this has nothing to do with their capability. It has everything to do with a fundamental misunderstanding about how understanding actually works. Think about the last time something genuinely fascinated you. Maybe it was figuring out how a car engine works, or understanding why certain chess moves are brilliant, or getting lost in how ancient civilizations built their temples. Notice what happened in your mind. You weren't just passively receiving information, you were actively grappling with it. You were asking questions, even if silently. You were trying to predict what comes next. You were noticing contradictions and trying to resolve them. Your brain was doing something, not just absorbing. Now compare that to how most people approach learning. They open a textbook and start reading. They attend a lecture and start listening. They assume their job is to transfer information from the page or the speaker into their memory, like pouring water from one container to another. And this is precisely where everything breaks down, because the brain doesn't work like an empty container waiting to be filled. It works like a living thing that grows by wrestling with its environment. Let me show you what happens when you try to learn passively. Imagine someone reads you a paragraph about how electricity works. You hear the words. You might even understand each sentence as it passes by. But 5 minutes later, if someone asks you to explain it, you find yourself grasping at shadows. The information never actually became part of you. It just moved through your awareness like scenery passing by a train window. You were present, but you weren't engaged in the kind of mental activity that builds understanding. Here's the key principle that changes everything. The brain only truly learns what it has to actively reconstruct, not what it hears, not what it reads. What it builds for itself, piece by piece, through its own effort. This isn't a metaphor. This is how the neural machinery actually operates. When you passively receive information, you're using one set of mental processes. When you actively try to figure something out, you engage an entirely different system, one that forms lasting connections and genuine understanding. So what does this mean practically? It means you need to transform every learning situation into a problem-solving situation. Before you read about how something works, you should wonder how it might work. Before you study a solution, you should struggle with the problem. Before you accept an explanation, you should notice what puzzles you about it. This sounds simple, but it requires a complete reversal of how most people approach learning. Let's take a concrete example. Suppose you need to understand how levers work. The typical approach is to read the explanation, look at the diagrams, memorize the principle that force times distance on one side equals force times distance on the other side. Maybe you can even solve some textbook problems by plugging numbers into the formula. But do you really understand it? Here's a test. Can you explain why a long lever is stronger than a short one without using any equations? Can you predict what would happen with a lever that has uneven thickness? Can you figure out whether it would be easier to lift a rock with the fulcrum close to you or close to the rock? If you can't answer these immediately, it's not because... What if the reason you hate learning isn't because your brain is lazy, but because you've been forcing it to work against its nature? Most people spend years trying to make themselves interested in things they should learn. They sit down with textbooks, tell themselves to focus, and wonder why their minds keep wandering. They assume learning is supposed to feel like discipline, like lifting weights for the mind. But there's something fundamentally wrong with this picture. The brain doesn't need to be forced to love learning. It already does. Watch a child spend hours figuring out how a door latch works, or how to stack blocks higher without them falling. Nobody taught them to be curious about these things. Nobody rewarded them for caring. They simply encountered a puzzle, and their minds locked onto it like a magnet. The question isn't how to make your brain love learning. The question is, what are you doing that's killing this natural drive? Here's the uncomfortable truth. When people say they hate learning, what they actually hate is the feeling of information sliding off their minds like water off glass. They hate reading a page and realizing they absorbed nothing. They hate sitting in lectures where words turn into noise. And so they conclude that they're not good at learning, or that certain subjects just aren't for them. But this has nothing to do with their capability. It has everything to do with a fundamental misunderstanding about how understanding actually works. Think about the last time something genuinely fascinated you. Maybe it was figuring out how a car engine works, or understanding why certain chess moves are brilliant, or getting lost in how ancient civilizations built their temples. Notice what happened in your mind. You weren't just passively receiving information, you were actively grappling with it. You were asking questions, even if silently. You were trying to predict what comes next. You were noticing contradictions and trying to resolve them. Your brain was doing something, not just absorbing. Now compare that to how most people approach learning. They open a textbook and start reading. They attend a lecture and start listening. They assume their job is to transfer information from the page or the speaker into their memory, like pouring water from one container to another. And this is precisely where everything breaks down, because the brain doesn't work like an empty container waiting to be filled. It works like a living thing that grows by wrestling with its environment. Let me show you what happens when you try to learn passively. Imagine someone reads you a paragraph about how electricity works. You hear the words. You might even understand each sentence as it passes by. But 5 minutes later, if someone asks you to explain it, you find yourself grasping at shadows. The information never actually became part of you. It just moved through your awareness like scenery passing by a train window. You were present, but you weren't engaged in the kind of mental activity that builds understanding. Here's the key principle that changes everything. The brain only truly learns what it has to actively reconstruct, not what it hears, not what it reads. What it builds for itself, piece by piece, through its own effort. This isn't a metaphor. This is how the neural machinery actually operates. When you passively receive information, you're using one set of mental processes. When you actively try to figure something out, you engage an entirely different system, one that forms lasting connections and genuine understanding. So what does this mean practically? It means you need to transform every learning situation into a problem-solving situation. Before you read about how something works, you should wonder how it might work. Before you study a solution, you should struggle with the problem. Before you accept an explanation, you should notice what puzzles you about it. This sounds simple, but it requires a complete reversal of how most people approach learning. Let's take a concrete example. Suppose you need to understand how levers work. The typical approach is to read the explanation, look at the diagrams, memorize the principle that force times distance on one side equals force times distance on the other side. Maybe you can even solve some textbook problems by plugging numbers into the formula. But do you really understand it? Here's a test. Can you explain why a long lever is stronger than a short one without using any equations? Can you predict what would happen with a lever that has uneven thickness? Can you figure out whether it would be easier to lift a rock with the fulcrum close to you or close to the rock? If you can't answer these immediately, it's not because levers are complicated. It's because you never actually built an understanding of levers in your mind. You only memorized facts about levers. And facts without understanding are like having a map of a city you've never visited. You know where things are supposed to be, but you can't actually navigate. Now here's how you would approach the same topic differently. Before reading anything, you would play with the idea. You would imagine pushing down on a seesaw and think about what determines how much force you need. You would picture trying to pry open a stuck door and wonder why a longer stick helps more than a shorter one. You would make predictions, even wrong ones. You would confuse yourself with edge cases. Only then would you look at the explanation, not as truth delivered from above, but as someone else's solution to the same puzzles you've been wrestling with. This completely changes the experience. When you read the explanation now, you're not passively receiving it. You're testing it against your own thinking. You're seeing where it confirms your intuitions and where it surprises you. You're noticing what it clarifies and what it leaves mysterious. The information doesn't just sit in your memory. It connects to a whole web of active thinking you've already done. It becomes part of how you see the world. This principle applies to everything, but people resist it for a simple reason. It feels inefficient. Why should you waste time wondering about something when you could just read the answer? Why struggle when you could simply be told? This is the trap. It feels like struggling with a problem before seeing the solution is extra work. But it's not extra work. It's the only work that actually produces understanding. Everything else is just the illusion of learning. Think about what happens in a typical classroom. A teacher explains a concept clearly. The students nod along. Everything makes sense while it's being explained. But the next day, when they try to use that concept on their own, they discover they can't. They understood the explanation, but they never developed the ability to think with the idea. Understanding someone else's reasoning and being able to reason for yourself are completely different things. The brain needs to fail before it can succeed. It needs to wonder before it can comprehend. It needs to be confused before clarity means anything. When you shortcut this process by going straight to the answer, you're not saving time. You're guaranteeing that you'll have to relearn the same thing again and again because it never properly took root the first time. Here's another layer to this. The act of struggling to understand something does more than help you learn that particular thing. It trains your mind to become a better learning machine in general. Every time you face confusion and push through it, you're building mental tools that work across every domain. You're learning how to notice what you don't understand, how to break complex things into simpler pieces, how to test your understanding against reality, how to recognize when an explanation is genuinely clear versus when it's just confident-sounding nonsense. These meta skills are more valuable than any particular fact you might learn, because facts become outdated or irrelevant, but the ability to grapple with new ideas, to teach yourself, to think clearly about unfamiliar subjects, this stays with you. And you can't develop it by passively consuming information. You can only develop it by repeatedly placing yourself in situations where you have to figure things out. Now, let's talk about why this makes learning actually enjoyable instead of tedious. Remember, the brain is naturally curious, but curiosity isn't triggered by being told answers. It's triggered by encountering mysteries. When you approach learning by first wondering, by first trying to figure things out, you're activating that natural curiosity. Your mind becomes engaged not because you're forcing it to be interested, but because you've given it something it instinctively wants to do: solve puzzles. This is why children learn so naturally. They don't separate learning from playing. They encounter something puzzling. They mess around with it. They form theories. They test them. They update their understanding. It's all one continuous process of active engagement. Somewhere along the way, formal education convinced us that real learning means sitting still, absorbing information, and proving we remember it. But this is almost the opposite of how the mind actually builds understanding. Let's apply this to reading a difficult book. Most people open the book and start at page 1, reading linearly, trying to absorb each section before moving to the next. They treat the book like medicine, something to be taken in prescribed doses. But think about what happens when you read this way. You encounter a difficult idea, you don't quite grasp it, but you keep reading because you don't want to fall behind. You tell yourself you'll understand it later. The difficult idea becomes one of many things you're sort of following but not really grasping. Now, imagine a different approach. You open the book, but instead of reading to absorb, you're reading to notice what puzzles you. When you hit something you don't understand, you stop. You don't keep reading. You engage with the confusion. You try to articulate exactly what doesn't make sense. You flip back to earlier sections. You think about whether the author's claim could be wrong or whether you're missing something. You try to explain the idea to yourself in simpler terms. Only when you've genuinely worked through the difficulty do you continue. This might mean you read 10 pages in the time most people read 50, but those 10 pages actually become part of how you think. The other approach gives you the comforting feeling of progress, but when the book is finished, almost nothing remains. You can't explain the key. What if the difference between ordinary thinking and genius thinking isn't about being born with a special brain, but about using the brain you already have in a completely different way? Most people assume that brilliance is something you either have or you don't. They look at great minds throughout history and think these individuals possess some rare gift that sets them apart from everyone else. But this assumption misses something fundamental about how the human mind actually works. The brain isn't a static object with fixed capabilities. It's more like a muscle that changes based on how it's used. And the way most people use their minds keeps them trapped in patterns that prevent genuine understanding. Here's the real problem. When people encounter something difficult to understand, they typically do one of two things. Either they memorize facts and formulas without really grasping what those facts mean, or they give up entirely, convinced the material is beyond their abilities. Both approaches stem from the same mistaken belief that understanding is something that happens to you rather than something you actively create. Think about a typical classroom where students are learning mathematics. The teacher writes equations on the blackboard. Students copy these equations into their notebooks. They practice problems until they can reproduce the steps. When the test comes, they retrieve what they've memorized and write it down. Some students do well on the test, others struggle. But here's what almost no one realizes. Even the students who score highly often don't truly understand what they're doing. They've learned to follow a recipe, but they haven't grasped why the recipe works. This is the difference between knowing and understanding. Knowing means you can reproduce information. Understanding means you can explain why that information is true, how it connects to other ideas, and what would happen if you change something fundamental about it. The human mind is capable of extraordinary understanding, but most people never develop this capacity because they confuse memorization with comprehension. So, how does someone actually rewire their thinking to operate at a higher level? The first principle is deceptively simple. Never move forward until you can explain something in the simplest possible terms. This doesn't mean dumbing things down. It means stripping away all the complex language and getting to the core of what's actually happening. Imagine a student struggling with basic physics, trying to understand why objects fall to the ground. The textbook might say that gravity is a force that attracts masses toward each other, with the force proportional to the product of the masses and inversely proportional to the square of the distance between them. A student could memorize this definition. They could even plug numbers into the formula and calculate correct answers. But do they understand gravity? Real understanding comes when that student can close the textbook and explain, in their own words, what gravity actually does. Not using the textbook's language, but describing it as if talking to someone who's never heard of gravity before. Maybe they'd say something like, There's something about having mass that makes objects pull on each other. The bigger the objects, the stronger the pull, and the farther apart they are, the weaker it gets. That's understanding. That's what it sounds like when someone has actually grasped a concept rather than just memorized words. This brings us to the second principle. Break everything down into smaller pieces until each piece is completely obvious. The brain doesn't handle complexity well when it tries to grasp everything at once, but it's remarkably good at understanding simple things and then building up from there. Consider someone learning to read music. Looking at a full orchestral score can be overwhelming. There are multiple staffs, different clefs, various instruments, all playing different notes simultaneously. Someone who tries to understand all of this at once will feel lost. But what if they start with just one note? A single note on a staff is simple. Anyone can understand that. Then they add another note. Still manageable. Then they understand how these two notes relate to each other. They build up, piece by piece, until eventually they can look at that orchestral score and hear in their mind what it will sound like when played. The genius mind doesn't work faster or hold more information. It works by breaking problems down until each component is trivially simple, then building up understanding from those simple pieces. This is why truly brilliant people can often explain complex ideas in ways that make them seem obvious. They've done the hard work of decomposition, so they can show others the simple building blocks that underlie apparent complexity. The third principle might seem counterintuitive. Spend more time thinking about what you don't understand than what you do understand. Most people do the opposite. They focus on the parts that make sense and skim over the confusing parts, hoping understanding will come later. It rarely does. The confusing parts are where actual learning happens. Picture a mathematician working through a proof in a textbook. They read the first few lines and follow the logic. Then they hit a step that says, "It follows that," or "therefore," before jumping to a conclusion that isn't immediately obvious. Most readers would keep going, assuming the author must be right, but someone developing real understanding would stop. They'd spend time, maybe hours, figuring out exactly how that conclusion follows from the previous statements. They might fill pages with their own work, trying different approaches until suddenly the connection becomes clear. This is uncomfortable. The human mind naturally wants to feel competent and move forward. Dwelling on confusion feels like failure, but this discomfort is precisely where the brain is doing its most important work. When you struggle with something that doesn't make sense, your brain is actively building new connections, trying to integrate this new information with what you already know. Skip over the confusion, and those connections never form. The fourth principle addresses how different concepts relate to each other. Real understanding isn't about knowing lots of isolated facts. It's about seeing how everything connects. The genius mind is constantly asking, how is this like something I already understand? How is it different? What happens if I change this assumption? Could I arrive at the same conclusion from a different starting point? Think about someone studying history. They could memorize dates and events, learning that one war started in a particular year, a treaty was signed in another year, an empire fell in yet another year. That's a collection of facts. But understanding history means seeing patterns. It means recognizing that certain conditions tend to lead to conflict, that economic pressures drive political decisions, that ideas spread and evolve and shape societies. Someone with this kind of understanding doesn't need to memorize as much because they can reason their way through historical developments using general principles. This applies to every subject. In literature, it's not about memorizing plot summaries, but understanding how character motivations drive narrative. In chemistry, it's not about memorizing reactions, but understanding how molecular structure determines behavior. In music, it's not about memorizing finger positions, but understanding how harmony and melody interact. The connections between ideas carry more weight than the ideas themselves. Now, here's what's actually happening in the brain when someone thinks this way. The human brain contains billions of neurons that communicate through connections called synapses. When you learn something new, you're not adding information to some mental filing cabinet. You're creating new patterns of connections between neurons. The strength of understanding depends on how many connections you build and how strong those connections are. When someone memorizes without understanding, they're creating isolated connections. The brain links a question to an answer, a problem type to a solution method. These connections are fragile. They don't integrate with the rest of what that person knows. They're easily forgotten because nothing supports them or reinforces them. But when someone truly understands, they're building a rich network of interconnected ideas. Each concept links to multiple other concepts. When they think about one idea, related ideas naturally come to mind. The understanding is robust because it's supported by this network. Even if they forget specific details, they can often recreate those details by reasoning from what they do remember. This is why explaining something in your own words is so powerful. When you articulate an idea, you're forcing your brain to pull together all the relevant connections and organize them into a coherent structure. If you can't explain something clearly, it means those connections aren't well formed yet. The act of trying to explain actually strengthens and clarifies the connections. The same thing happens when you tackle a problem from multiple angles. Each approach you try builds new connections. Even approaches that don't work out contribute to understanding because they help you see why certain paths lead nowhere. Someone who's solved a problem in only one way has learned that specific solution. Someone who's tried 10 different approaches and found 3 that work has developed genuine mastery. There's something else that happens in a mind that thinks this way. It becomes comfortable with uncertainty. Most people feel anxious when they don't know something. They want immediate answers. They grab onto the first explanation that makes some sense, even if it's superficial. But truly powerful thinking requires sitting with not knowing, exploring possibilities, following threads of reasoning to see where they lead. Picture a scientist in a laboratory running experiments. The experiments don't always work. In fact, they usually don't work the first time, or the second time, or even the 10th time. But each failed experiment provides information. It rules out certain possibilities. It suggests new questions to investigate. Someone who can't tolerate this uncertainty, who needs every experiment to succeed, will never make important discoveries. The breakthroughs come from being willing to work in the space of not knowing. This same principle applies to any kind of learning. When reading a difficult book, there will be passages that don't make sense on first reading. Someone with a rigid mind gets frustrated and gives up. Someone with a flexible mind sees this as normal. They reread, they think about it, they keep going and come back later. They trust that understanding will emerge through engagement with the material. The practical application of all this is actually quite straightforward, though it requires discipline. When approaching any subject, start by identifying the simplest possible foundation. What are the absolute basics that everything else builds upon? Make sure those basics are crystal clear before moving forward. Let's say someone wants to learn about electricity. They might be tempted to jump straight into circuits and components and calculations, but the foundation is much simpler. Electricity is about the movement of charged particles. That's it. Spend time really understanding what that means. What is charge? What makes charged particles move? Once this foundation is solid, everything else becomes much easier because it all flows from this simple beginning. As new concepts are introduced, constantly relate them back to what's already understood. Don't just accept that resistors reduce current flow. Ask why. What's actually happening at the physical level that causes this? How does this relate to the fundamental idea that electricity is moving charges? Build those connections explicitly. When something doesn't make sense, stop. Don't push forward hoping it will become clear later. Work on that confusion until it resolves. Try explaining it out loud, as if teaching someone else. Draw diagrams. Make up your own examples. Approach it from different directions. The time spent here isn't wasted. This is where real learning happens. Practice explaining concepts in multiple ways. If you understand something deeply, you should be able to describe it using different analogies, different examples, different levels of detail. Someone who can only explain something one way, using the exact words from the textbook, hasn't truly made it their own. Look for connections between different subjects. Mathematics and music have deep. What if the difference between ordinary thinking and genius thinking isn't about being born with a special brain, but about using the brain you already have in a completely different way? Most people assume that brilliance is something you either have or you don't. They look at great minds throughout history and think these individuals possess some rare gift that sets them apart from everyone else. But this assumption misses something fundamental about how the human mind actually works. The brain isn't a static object with fixed capabilities. It's more like a muscle that changes based on how it's used. And the way most people use their minds keeps them trapped in patterns that prevent genuine understanding. Here's the real problem. When people encounter something difficult to understand, they typically do one of two things. Either they memorize facts and formulas without really grasping what those facts mean, or they give up entirely, convinced the material is beyond their abilities. Both approaches stem from the same mistaken belief that understanding is something that happens to you rather than something you actively create. Think about a typical classroom where students are learning mathematics. The teacher writes equations on the blackboard. Students copy these equations into their notebooks. They practice problems until they can reproduce the steps. When the test comes, they retrieve what they've memorized and write it down. Some students do well on the test, others struggle. But here's what almost no one realizes. Even the students who score highly often don't truly understand what they're doing. They've learned to follow a recipe, but they haven't grasped why the recipe works. This is the difference between knowing and understanding. Knowing means you can reproduce information. Understanding means you can explain why that information is true, how it connects to other ideas, and what would happen if you change something fundamental about it. The human mind is capable of extraordinary understanding, but most people never develop this capacity because they confuse memorization with comprehension. So, how does someone actually rewire their thinking to operate at a higher level? The first principle is deceptively simple. Never move forward until you can explain something in the simplest possible terms. This doesn't mean dumbing things down. It means stripping away all the complex language and getting to the core of what's actually happening. Imagine a student struggling with basic physics, trying to understand why objects fall to the ground. The textbook might say that gravity is a force that attracts masses toward each other, with the force proportional to the product of the masses and inversely proportional to the square of the distance between them. A student could memorize this definition. They could even plug numbers into the formula and calculate correct answers. But do they understand gravity? Real understanding comes when that student can close the textbook and explain, in their own words, what gravity actually does. Not using the textbook's language, but describing it as if talking to someone who's never heard of gravity before.
Let me be honest with you. You think you understand things, but most of what you carry in your head is just labels, words. They sound impressive. They shut down questions. They give authority without earning it. But if you strip the language away and nothing meaningful remains, then the understanding was never there. It was decoration, a costume worn by ignorance to look intelligent. Here's the uncomfortable part. Most education systems reward this behavior. You're taught to recognize the right answers, not to wrestle with the problems. You're trained to pass tests, not to challenge assumptions. So you grow up believing that knowing the correct terminology means you know the subject. It doesn't. It just means you've been exposed to it. Real understanding begins where memorization fails. It begins the moment you ask a question that doesn't have a clean answer. It begins when you try to explain an idea in simple terms and realize you can't. That moment of failure is not a sign that you're stupid. It's proof that you're finally touching the edge of what you don't know, and that edge is where thinking actually starts. The mind loves certainty because certainty feels safe, but certainty is often a shortcut, a way to stop investigating. The moment you become emotionally attached to an explanation, you stop testing it. You defend it instead. You look for agreement rather than evidence. And slowly, without noticing, curiosity is replaced by belief. Belief is easy. Understanding is hard. Understanding demands humility. It requires you to accept that your current explanation might be incomplete or wrong or useful only in limited situations. It forces you to separate what you wish were true from what actually survives contact with reality. That process is uncomfortable, which is why so few people commit to it. Instead, they lean on authority. Someone famous said it. A book stated it. A teacher explained it. That may be a starting point, but it is never the finish line. Reality does not recognize credentials. It only responds to accurate descriptions. If two explanations compete, the one that predicts outcomes more reliably wins. Not because it sounds better, not because it's older, not because more people repeat it, but because it works. That's the only standard that matters. And this is where most people quietly fail. They never test their understanding. They never ask what would happen if this were wrong. They never try to break their own ideas. They protect them, they decorate them, they repeat them louder. But ideas don't become stronger through protection. They become stronger through pressure. If you can't explain an idea without hiding behind jargon, you don't own it. If you can't answer basic questions without getting defensive, you don't understand it. And if you can't admit uncertainty, you've already stopped learning. The goal is not to sound intelligent. That's a shallow ambition. The goal is to see more clearly. And clarity often looks simple, even obvious, once you finally reach it. Not because it was easy, but because confusion has been removed. So here is the challenge you should carry with you. Whenever you learn a new concept, strip the words away and ask what remains. Ask what it explains, what it predicts, what it fails to explain. Ask where it breaks. Ask how you would know if it were wrong. Do this consistently, and your confidence will shrink, but your understanding will grow. You'll speak less, you'll listen more. You'll be slower to declare certainty and faster to ask better questions. That's not weakness. That's intellectual strength. Because the person who knows the limits of their understanding is far more dangerous, in the best possible way, than the person who merely knows the right words. And until you learn that difference, you don't understand reality. You just recognize its names. Certainty is often the enemy of truth because the moment you become absolutely sure, you stop looking. You close the door, not because you've reached the end of understanding, but because certainty feels comfortable. It gives the mind a place to rest. And when the mind rests, inquiry dies. Truth is not offended by questions. False ideas are. That alone should make you suspicious of anything that demands loyalty instead of examination. Real understanding invites pressure. It survives doubt. It improves when challenged, but certainty behaves differently. It protects itself. It resists testing. It treats questions as threats rather than tools. Most people don't realize when certainty takes over because it disguises itself as confidence. Confidence sounds strong. It feels decisive. It's rewarded socially. But confidence without continuous testing is just frozen thinking. It's an opinion that stopped evolving. The world does not work that way. Reality keeps changing, or at least revealing new layers of itself. Explanations that once worked may fail under new conditions. Ideas that were useful approximations can become misleading if treated as absolute. Truth is not a trophy you win once and keep forever. It's a process, an ongoing conversation with reality. Certainty interrupts that conversation. When you're certain, you stop asking why and start saying because. You stop listening for signals that contradict you. You reinterpret evidence to protect your belief instead of adjusting your belief to fit the evidence. That's not understanding, that's maintenance. And the most dangerous certainty is not loud arrogance. It's quiet confidence, the kind that never feels the need to question itself, the kind that says this is how it is and moves on. That mindset blocks discovery not by force but by satisfaction. History is full of ideas that were once held with absolute certainty and later collapsed under simple observation. They didn't fall because people were stupid. They fell because people were convinced they were finished thinking. Every major correction in human understanding began with someone saying, "I'm not convinced," or "something doesn't fit." Those statements don't come from certainty. They come from doubt. Doubt is not the opposite of knowledge, it's the engine of it. Doubt creates movement. It keeps ideas flexible. It allows you to hold explanations lightly, ready to replace them when better ones appear. Without doubt, learning becomes memorization and progress becomes repetition. But doubt is uncomfortable. It leaves questions open. It resists closure. That's why certainty is attractive. It offers psychological relief. It lets you stop struggling with uncertainty and declare victory. The problem is, truth doesn't care about your comfort. Nature doesn't adjust itself to match your beliefs. It doesn't reward conviction. It rewards accuracy. And accuracy requires constant adjustment. The moment you believe your explanation is final, you stop making those adjustments. This is why the smartest thinkers are often the least certain. not because they know less, but because they see more. They recognize the gaps. They understand the assumptions hidden inside their explanations. They know where their models work, and where they don't say, this is the truth. They say, this works so far. That small difference changes everything. Certainty turns ideas into identities. Once that happens, questioning the idea feels like a personal attack. Evidence becomes an enemy. Criticism becomes disrespect. And truth becomes secondary to self-protection. At that point, learning is no longer the goal. Winning arguments has nothing to do with understanding reality. If you want to get closer to truth, you have to make peace with uncertainty. You have to accept that your current understanding is provisional, useful perhaps, effective maybe, but never final. That doesn't mean you drift without conclusions. It means you hold conclusions with humility. You use them, test them, and remain willing to abandon them when they fail. Certainty shuts down that flexibility. It replaces curiosity with defense. It trades exploration for stability. And while stability feels good, it quietly erodes the very thing that led you to understanding in the first place. So the real danger of certainty is not that it's wrong. It's that it prevents you from discovering when it is. The truth does not require you to believe in it. It requires you to keep checking. Authority does not equal correctness, and confusing the two is one of the fastest ways to stop thinking. The moment a statement is accepted because of who said it rather than why it works, understanding takes a back seat. Titles replace testing. Reputation replaces reasoning. And slowly, without noticing, judgment is outsourced. Authority feels efficient. It saves time. You don't have to struggle through uncertainty or verify claims yourself if someone important has already spoken. That shortcut is tempting, especially in complex subjects where the effort required to check things feels overwhelming. But convenience is not truth, and mental laziness has never produced. Insight, reality does not recognize rank. It doesn't care about degrees, awards, or confidence. If an explanation is wrong, it will fail no matter who proposed it. If it's right, it will work even if it came from an unknown voice. Nature does not negotiate with authority. The danger begins when respect turns into obedience. Respect is reasonable. You listen carefully to people with experience. You consider their ideas seriously. Obedience is different. Obedience means suspending your own judgment. It means accepting conclusions without understanding the reasoning behind them. That's not learning, that's submission. Many people mistake disagreement with disrespect. They think questioning an expert is arrogance. It's not. Refusing to question is negligence. If an idea is solid, it will survive scrutiny. If it collapses when questioned, authority was the only thing holding it up. History is a record of authoritative certainty being corrected by careful doubt. For long periods, confident experts were wrong, not because they lacked intelligence, but because they trusted established answers more than observed reality. Progress didn't come from louder credentials. It came from people willing to check. Authority tends to protect itself. Once a system of ideas becomes institutionalized, challenges are treated as threats rather than opportunities. Dissenters are dismissed, not evaluated. But truth doesn't advance by consensus. It advances by correction. The most reliable thinkers understand this. They don't ask who said it. First, they ask, how do we know? They care less about pedigree and more about evidence. They don't reject authority automatically, but they never surrender to it either. Blind trust creates fragile knowledge. It works only as long as no one tests it. The moment reality pushes back, the cracks appear. And when that happens, people who relied on authority instead of understanding are left confused, angry, or defensive. Understanding requires ownership. You must be able to trace an idea back to its foundations, see its assumptions, and recognize its limits. If you can't do that, then the idea isn't really yours. You're carrying it for someone else. This is why authority should guide curiosity, not replace it. Experts can point you toward useful questions, proven methods, and past failures, but they cannot think for you. The moment they do, learning stops. There is also a subtle arrogance hidden in blind obedience. It's the belief that someone else has already done all the necessary thinking, so you don't have to. That assumption is not humility, it's avoidance. True humility is acknowledging that no one is infallible. including the most respected voices in the room. It's recognizing that expertise increases reliability, not certainty. Even the best explanations are approximations, waiting to be improved or replaced. Authority becomes dangerous when it is treated as a shield against criticism. When someone says, "Trust me," instead of showing their reasoning, that's a warning sign. Truth does not need protection from questions. If you want to get closer to reality, learn to separate respect from acceptance. Listen carefully. Examine thoroughly. Agree conditionally. Disagree respectfully. And always reserve the right to change your mind. Because the moment you stop questioning authority, you stop participating in the search for truth. You become a spectator in someone else's understanding. And reality will eventually remind you that it never asked who was in charge. Questions are more valuable than answers because answers have an expiration date and questions do not. An answer can feel solid, complete, and satisfying, but that feeling is often an illusion. It gives the mind closure, and closure is where curiosity quietly dies. A good question, on the other hand, refuses to let you rest. It keeps pulling at the loose threads of your understanding. It exposes gaps you didn't know were there. And that discomfort is not a flaw, it's the signal that real thinking has begun. Answers are attractive because they feel like progress. You ask something, you receive a response, and your brain registers completion. But most answers are temporary solutions to deeper problems. They work within a limited context under certain assumptions at a particular level of detail. Treat them as final and they become obstacles. They stop you from noticing when conditions change or when the explanation no longer fits reality. A question does the opposite. It keeps the system open. When you ask a serious question, you are admitting that your current understanding is incomplete. That admission is powerful. It creates space for learning. It allows new information to enter without being filtered through the need to be right. A question doesn't demand loyalty, it demands exploration. Most people are trained to value answers early in life. School rewards correct responses, not interesting questions. Exams measure how well you can reproduce what's already known, not how deeply you can interrogate it. Over time, this trains the mind to chase closure instead of clarity. The habit becomes automatic. Get the answer, move on. But moving on too quickly is how shallow understanding survives. An answer can stop a conversation. A question can open 10 new ones. That's why progress, real progress, comes from questioning what seems obvious. Every major shift in understanding started with someone refusing to accept an answer that everyone else was comfortable with. Not because they wanted to be difficult, but because something didn't sit right. Questions are dangerous to weak ideas. That's precisely why they matter. If an explanation collapses under a simple question, it was never strong to begin with. Strong ideas don't fear questions, they depend on them. Each challenge refines them, sharpens their boundaries, reveals their limits. Without questions, ideas stagnate. They become slogans rather than two. Answers often create the illusion of mastery. You hear an explanation, you can repeat it, and suddenly you feel informed. But repetition is not understanding. Understanding shows itself when you can navigate unfamiliar situations, when you can predict outcomes, when you can recognize where an explanation applies and where it fails. Questions train that ability. Answers alone do not. There is also a deeper reason questions matter more. They keep you honest. An answer can be memorized without being examined. A question forces engagement. It requires you to confront uncertainty directly. It exposes how much of your confidence is borrowed. When you can't answer your own question, you are faced with a choice. Pretend you understand or admit that you don't. That moment separates performance from thinking. Most people choose performance. They collect answers like trophies. They quote them, defend them, build identities around them. And once an answer becomes part of who you are, questioning it feels like self-destruction. At that point, learning stops, not because there is nothing left to learn, but because curiosity has been sacrificed to self-protection. Questions don't let you hide that way. They strip away certainty. They force humility. They remind you that understanding is provisional, that explanations are tools, not truths carved into reality. This doesn't mean answers are useless. They are necessary. But they are not the destination. They are checkpoints, temporary resting places before the next question appears. The mistake is treating them as final. A mind focused on answers asks, what is the correct response? A mind focused on questions asks, what's really going on here? That difference changes everything. When you value questions, you listen differently. You notice inconsistencies, you pay attention to what doesn't fit. You become comfortable saying, I don't know yet, without feeling diminished by it. That comfort is not ignorance, it's intellectual maturity. The most dangerous phrase in thinking is that's settled. Nothing important ever truly is. Reality is too complex, too layered, too subtle for permanent closure. Every explanation is an approximation. Every model leaves something out. Questions keep those limitations visible. Without questions, answers harden into dogma. With questions, answers remain flexible, useful, and alive. So if you want depth, stop chasing closure. Stop collecting conclusions as if they were proof of intelligence. Start cultivating questions that make you uneasy, questions that challenge what you think you already know, questions that don't resolve quickly because answers may make you sound informed, but questions are what actually move you closer to understanding. If you can't explain it simply, you don't understand it, and no amount of confidence, credentials, or complex language will change that. Complexity is often mistaken for depth, but more often than not, it's camouflage. It hid. There's gaps in understanding behind impressive words and long explanations that sound intelligent while saying very little. When someone truly understands something, they don't need to protect it with confusion. They can walk straight through it clearly, step by step, without getting lost. Simplicity is not about dumbing things down. It's about stripping an idea to its core and seeing what actually holds it together. That process is brutally honest. It exposes every weak assumption, every borrowed explanation, every place where you've been pretending to understand instead of actually thinking. That's why people avoid it. It's far easier to repeat a complicated explanation than to build a simple one from scratch. When you explain something simply, you are forced to confront reality. You can't hide behind jargon. You can't lean on authority. You can't say, it just works that way and move on. You have to answer basic questions. What is happening? Why does it happen? What would happen if it didn't? Those questions are unforgiving. They don't care how educated you are. They don't care how many books you've read. They only care whether your explanation actually makes sense. Most people don't fail at understanding because the subject is too hard. They fail because they stop at the first explanation that sounds reasonable. They accept a description instead of building a mental model. They memorize conclusions without understanding the machinery underneath. As long as the explanation feels satisfying, they move on. That satisfaction is the trap. Real understanding feels different. It's quiet. It's precise. It allows you to predict outcomes and recognize when something doesn't fit. And it gives you the ability to explain the idea to someone else without relying on borrowed language. If you can't do that, you don't own the idea, you're renting it. Simple explanations are difficult because they require you to know what matters and what doesn't. They force you to distinguish the essential from the decorative. That takes work. It requires you to rethink the idea multiple times, each time removing unnecessary parts until only the structure remains. That structure is understanding. People often confuse simplicity with incompleteness. They think that a simple explanation must be missing something. Sometimes it is, but often what's missing is not truth, it's clutter. The mind loves clutter because it feels like progress. More details, more terms, more layers. But progress is not measured by how much you can say. It's measured by how clearly you can see. When an explanation is truly understood, it becomes flexible. You can approach it from different angles. You can explain it to different audiences. You can adjust it when new evidence appears. That flexibility comes from simplicity. Complex, fragile explanations break the moment conditions change. Simple ones adapt. There's another uncomfortable reason people avoid simple explanations. Simplicity makes you AC. Countable. If your explanation is clear, it can be tested. It can be challenged. Others can see exactly where it might fail. Complexity offers protection. It creates fog. In fog, mistakes are harder to spot. That's why simple explanations are often resisted, especially in intellectual environments. They threaten status. They remove the mystery that makes some people feel important. If everyone can understand the idea, then expertise has to be earned through accuracy, not presentation. Understanding something simply doesn't mean you ignore its depth. It means you understand the foundation well enough to build on it. Depth without clarity is not depth. It's confusion stacked on top of confusion. Clarity comes first. Complexity, when necessary, comes later. When you hear an explanation that leaves you more confused than when you started, don't assume the subject is too advanced. Consider the possibility that the explanation is bad. A good explanation increases understanding. It doesn't demand patience or faith. It earns trust by making sense. The discipline of simple explanation is a constant test. It forces you to revisit ideas you thought you understood and ask whether you really do. It exposes intellectual laziness. It separates genuine comprehension from polished repetition. If you want to know whether you understand something, try to explain it without notes, without jargon, and without rushing. If you get stuck, that's not a failure. That's feedback. It's telling you exactly where your understanding ends. And that's valuable information. Because understanding doesn't grow from pretending. It grows from identifying what you don't yet know and working patiently toward clarity. Simplicity is not the end of thinking. It's the proof that thinking is.
Have you ever finished reading a page, reached the end, and realized you have absolutely no idea what you just read? Your eyes moved across the words. You saw them. But somehow, nothing stayed. It's as if the information just passed through your mind like water through a sieve. This is one of the most frustrating experiences in learning. We read something important, something we need to know, and a day later it's gone. A week later, we might as well have never read it at all. So what's happening here? Why does our brain seem to let so much slip away? The answer isn't that we have bad memory. The problem is that we've misunderstood what memory actually is and how it works. Most people treat their brain like a recording device, like a camera that's supposed to capture everything it sees. But that's not how it functions, not even close. Think about the last time you walked through your house. You saw the furniture, the walls, the doors. But right now, could you describe the exact pattern of wear on your doorknob? Or the precise number of books on your shelf? You saw these things, but you didn't encode them. Your brain didn't store them because it didn't think they mattered. This is the first thing to understand. Your brain is not trying to remember everything. It's trying to remember what's important, and it decides what's important based on very specific signals. If we want to remember what we read, we need to understand these signals and work with them, not against them. Let's start with what actually happens when you read something. The words come in through your eyes. They get processed in the visual cortex. Then they're converted into meaning in the language centers of your brain. But here's the critical part. Just because information reaches your brain doesn't mean it gets stored there. It's like the difference between someone telling you something and you actually writing it down. The information was present, but was it recorded? Memory formation requires something more than just exposure. It requires encoding, and encoding doesn't happen automatically. It happens when your brain decides that the information is worth the energy it takes to store it. Because make no mistake, remembering things costs energy. Maintaining neural connections, strengthening synapses, integrating new information with old information, all of this requires resources. So your brain is selective. Think of it this way. Imagine you're walking through fresh snow. The first time you take a path, you leave footprints, but they're shallow. If it snows again, those footprints disappear. But if you walk the same path every day, eventually you create a clear trail. The snow gets packed down, the path becomes obvious. That's what happens with memory. A single exposure creates a faint trace. But repetition, and more importantly, engagement with the material, packs that path down. But here's where it gets interesting. Not all repetition is equal. You could read the same page 10 times passively, letting your eyes glide over the words, and still remember almost nothing. Why? Because your brain isn't interpreting passive reading as a signal that this information matters. There's no struggle, no effort, no connection being made. It's like walking the same path in the snow but stepping in slightly different places each time. You never reinforce the same trail. So what does work? What makes information stick? The answer lies in something called elaborative encoding. This is the process of connecting new information to things you already know, of transforming abstract concepts into concrete examples, of asking questions about what you're reading rather than just absorbing it. Let's say you're reading about how the heart pumps blood. If you just read the heart has 4 chambers and valves that prevent backflow, that's one kind of learning. It's abstract. It's isolated. But if you stop and think, wait, why 4 chambers? Why not 2 or 6? And these valves, they're like the check valves in plumbing that keep water from flowing backward. Now you're doing something different. You're connecting the new information to something you already understand. You're asking why things are the way they are. You're building mental models. This is what makes information memorable. Not repetition alone, but meaningful processing. Your brain stores things that it has worked with, manipulated, questioned, and connected. It's the difference between hearing a phone number once and dialing a phone number. When you dial it, you have to actively recall each digit, place it in sequence, and execute an action. That active retrieval is what creates strong memory traces. There's a principle in neuroscience called the generation effect. It shows that information we generate ourselves is remembered better than information we simply read. If you read a sentence like "the hungry man ate the pizza," you'll remember it somewhat. But if you read "the hungry man ate the" and have to supply the word yourself, you'll remember it much better. Why? Because generation requires retrieval. It requires you to search your memory, to activate related concepts, to create something rather than just receive it. This is why summarizing what you read in your own words is so powerful. When you close the book and try to explain the concept to yourself, you're forcing your brain to reconstruct the information from memory. And that reconstruction process, that's what creates strong, lasting memories. Every time you successfully retrieve something, you're strengthening the path to it. Now, there's another crucial element: understanding. True understanding creates memory almost automatically. Think about the difference between memorizing a series of random numbers and understanding why those numbers form a pattern. Random numbers are hard to remember because there's no structure, no meaning. But if you understand that the numbers are the Fibonacci sequence, where each number is the sum of the two before it, suddenly they're easy. You don't need to memorize each individual number because you understand the rule that generates them. This is why reading for understanding, not just for exposure, is so important. When you understand something deeply, when you grasp not just what happens, but why it happens, you're creating a compressed representation in your mind. Instead of storing 1,000 individual facts, you're storing the underlying principle that generates those facts. It's vastly more efficient. Consider how you remember stories versus how you remember lists. Stories are easy to remember because they have structure, cause and effect, character motivation, sequences that make sense. Lists are hard because they're arbitrary. There's no inherent connection between item 1 and item 2. This tells us something important. Our memory is designed for meaning, not for arbitrary information. So when you're reading, especially something dense or technical, the key is to constantly search for the meaning. Don't just read what happens, ask why it happens. Don't just accept a statement, think about what it implies. Does this new piece of information contradict something you thought before? Does it explain something you've been confused about? Does it connect to something in a completely different domain? These questions aren't extra work on top of reading. They are the work. They're what transforms reading from a passive activity into an active one. And active processing is what creates memory. There's also the matter of timing. Our brains consolidate memories in phases. When you first read something, it exists in what we call working memory. This is temporary, like RAM in a computer. It holds information just long enough for you to use it. But for information to move into long-term storage, it needs to be consolidated. And consolidation takes time. This is why cramming doesn't work well. You can shove information into working memory right before a test, and it might be there when you need it, but a week later, it's gone. It never got properly consolidated. The information never made it from that temporary storage into the stable long-term networks of your brain. What does work is spaced repetition. Instead of reading something once for an hour, you're better off reading it for 20 minutes, then coming back to it tomorrow, then again in 3 days, then again in a week. Each time you return to the material, you're forcing your brain to retrieve it, and retrieval is what strengthens memory. The spacing gives your brain time to consolidate between sessions. But here's what makes this even more effective. Each time you come back, don't just reread. Test yourself. Try to recall the main points before you look at them again. This retrieval practice is one of the most powerful learning techniques we know of. It feels harder than just rereading. It's supposed to. That difficulty is the signal your brain needs to recognize that this information is important. Think about learning to ride a bicycle. You can watch videos of people riding bikes. You can read about balance and momentum. But you won't learn until you actually get on the bike and struggle with it. The struggle, the wobbling, the near falls, these aren't obstacles to learning. They are learning. Your brain learns by doing, by failing, by correcting. The same is true for intellectual learning. The struggle to recall, the effort to reconstruct, the work of generating answers. This is what creates lasting memory. Now, let's talk about something subtle but important. Context and cues. Memories aren't stored in isolation. They're stored in networks connected to all sorts of contextual information. Where were you when you learned something? What were you thinking about? What else was happening? All of these become cues that can trigger the memory later. This is why it's easier to remember something in the same environment where you learned it. The room, the lighting, even the smell, these all become associated with the memory. But here's the problem. If you only study in one place, your memory becomes dependent on those cues. And when you need to recall the information somewhere else, it's harder. The solution is to vary your learning environment. Read in different places. Review material in different contexts. This forces your brain to encode the information more abstractly, less tied to specific cues. It makes the memory more flexible, more robust, more accessible from different mental states. There's also the question of depth. You can read something at a surface level, understanding the basic gist, or you can read it deeply, wrestling with implications and connections. Deep processing creates stronger memories. It's the difference between recognizing a face and knowing a person. Recognition is shallow, you know you've seen them before. Knowing is deep, you understand their personality, their history, their quirks. When you read, aim for knowing, not just recognizing. This means pausing frequently. It means asking questions. What's the author really saying here? Why is this point important? How does this relate to what came before? Could this be explained differently? Do you agree with this? Why or why not? These questions might slow down your reading speed, but they dramatically increase what you retain. And here's something interesting. Over time, as you get better at this kind of active reading, it doesn't slow you down as much. You develop the skill of reading and thinking simultaneously. The questioning becomes automatic. You start to notice patterns more quickly, make connections more easily. Your understanding accelerates. Let's consider one more aspect, the role of emotion. We remember things better when they're emotionally significant. A dramatic story sticks more than a dry recitation of facts. Why? Because emotion is one of the brain signals that something matters. When you feel something, curiosity, surprise, confusion, excitement, your brain pays more attention. It encodes more deeply. This doesn't mean you need to artificially manufacture emotion while reading, but it does mean that staying engaged, staying curious, allowing yourself to be surprised or puzzled, these states facilitate memory. If you're bored, if you're just going through the motions, your brain interprets that as a signal that this information isn't important. It allocates fewer resources to encoding it. So if you find yourself bored while reading something you need to remember, that's a problem to solve, not just a mood to tolerate. Can you approach the material differently? Can you find a question within it that genuinely interests you? Can you look for connections to something you do care about? Sometimes the key to remembering isn't technique, it's finding a way to genuinely engage with the material. All of this points to a central truth about memory. It's not a passive recording, it's an active reconstruction. Every time you remember something, you're rebuilding it from pieces. And the act of rebuilding it changes it slightly, strengthens certain connections, weakens others. Your memory is alive, dynamic, constantly being reshaped by how you use it. This means that the best way to remember what you read is to use it, write about it, explain it to someone else, apply it to a problem you're trying to solve. Think about how it changes what you believed before. Let it interact with other things, you know. Every time you actively work with the information, you're strengthening it, integrating it more deeply into your web of knowledge. The person who reads a book and then closes it, moving on to the next thing, will forget most of it. The person who reads a book and then spends time thinking about it, discussing it, applying its ideas, will remember it for years. The difference isn't in the reading itself, it's in what happens after. Here's the beautiful part. Once you understand how memory works, you stop fighting against your brain. You work with it. You recognize that forgetting is natural and expected when you don't give your brain the signals it needs. You understand that difficulty during learning isn't a sign you're doing something wrong. It's often a sign you're doing something right. That struggle to recall, that effort to connect ideas, that work of generating rather than just receiving, this is what builds lasting knowledge. Memory isn't about having a better brain. It's about using your brain the way it's designed to be used. And it's designed for meaning, for connection, for active engagement. Give it those things and you'll be amazed at what stays with you. Not because you have a special gift, but because you're working with the natural mechanisms of how learning happens. The next time you pick up something to read, something you want to remember, don't just read it. Engage with it, question it, connect it, reconstruct it in your own words. Come back to it, test yourself on it. Let it change how you think about other things. Treat reading not as a task to complete, but as a conversation to have with ideas. Do this, and you won't need tricks or mnemonics for most of what you read. Understanding itself will be your memory. The ideas will stick not because you forced them to, but because they became part of how you think. And that's not just better memory. That's actual learning.
Every time you seek approval, your worth becomes a hostage to someone else's opinion. And the strange thing is, the more you try to please the world, the more the world ignores you. Life begins to lose its brightness when you live to be seen instead of living to understand. Now imagine just for a moment that all the energy you spend trying to be accepted was redirected into learning, into exploring, into understanding how things truly work. Imagine the power that would have.
You'd start to see the hidden beauty in simple things, in sound, in light, in ideas, in people. Because true genius isn't born from the desire to be admired, but from curiosity, that pure restlessness that makes you want to discover why things are the way they are. And when you dive into that curiosity, life starts to flow in a way that no ambition can ever reproduce. The truth is, the pursuit of recognition is a trap disguised as motivation. It pushes you to run faster, to work harder, to achieve more, yet it never lets you rest. It's a bottomless pit, and you know what's at the bottom of that pit? Nothing but emptiness. The emptiness of someone who lived to be remembered instead of living to understand. So listen closely. Living for the love of understanding is the only path that truly sets you free, because the pleasure of discovering is the reward itself, and the one who learns for the joy of learning never needs applause. Pay attention to me now, because what I'm about to tell you might completely change the way you see life. You've spent far too long trying to be recognized, trying to prove something to others, and without realizing it, you became a prisoner of that need. But let me tell you this, most of the people who seem to be winning are actually losing silently. They collect titles, possessions, praise, yet they lose something invisible, their inner freedom. They live like actors on a stage, playing a role the world wrote for them. But you know the problem? When the curtain falls, there's only silence. And in that silence, the question no one wants to face appears. Why am I doing all this? If your reason is to be recognized, you'll never rest. Because recognition is volatile. It shifts with people's moods, with trends, with the tides. One day they applaud you, the next they forget you. And if your worth depends on that, you're doomed to rise and fall with the world around you. But when you do something for the simple joy of understanding, something inside you changes. Suddenly time moves differently. You stop chasing, and you start being guided by something deeper. Curiosity. Curiosity is the engine of life. It turns boredom into discovery, pain into learning, chaos into meaning. When you follow that energy, you no longer need recognition, because the pursuit itself becomes fulfilling. It's the joy of understanding what lies behind things, of seeing how everything connects. That is true power. When you learn for the love of comprehension, the entire world opens before you. You stop being an actor, and you become the author. And for the first time, life starts to make sense. But to reach that point, you must do something few ever dare. Stop trying to be someone, and start trying to understand something. The difference seems small, but it's enormous. The first path enslaves you. The second one sets you free. Pay attention to me now, because I want to take you to a place where very few have the courage to look. People think freedom means being able to do whatever they want, but that's just the reflection of modern ignorance. True freedom is being able to think whatever you want, to doubt what you've been taught, and to allow yourself not to know. A mind that seeks recognition is enslaved by certainty. A mind that seeks understanding is free to explore. Do you want to know what truly destroys genius? The need to appear intelligent. The person who tries to look smart for others will never be truly intelligent, because they're focused on displaying, not discovering. Genius is born the moment you abandon the desire to be special and embrace the joy of uncovering the obvious. Think about it. Everything you know was once obvious to someone who had the courage to look closely. The difference between the mediocre and the brilliant doesn't lie in talent. It lies in genuine curiosity. The mediocre wants to be right. The brilliant wants to learn, even if it means stripping away their own vanity. And here's the irony. The more you care about what others think, the less you actually think for yourself. A curious mind is like a child taking apart a toy just to see what's inside. It doesn't crave status. It doesn't want applause. It wants the mystery. It wants the why. And that's what keeps the inner fire alive. The sincere desire to understand the world before the world understands you. Life becomes light when you realize you don't need to impress anyone. You begin to do things for the simple pleasure of seeing what happens. And strangely enough, that's when everything starts to work. When you stop chasing results, the results begin to chase you. Because the universe responds to genuine curiosity, not to empty ambition. The secret isn't to be recognized, it's to be so deeply immersed in the process that recognition becomes irrelevant. The reward lies in the very act of understanding.
And those who live that way exist in a state of freedom that money and status could never buy. Now imagine something uncomfortable yet necessary. What if most of human suffering didn't come from lack, but from excess? The excess of wanting, proving, showing. The world taught you that ambition is a virtue, but forgot to warn you that blind ambition is poison. You run, you exhaust yourself, you achieve, and when you finally arrive where you always wanted to be, you realize there's no one there, not even you. People confuse purpose with performance. They crave meaning, yet spend their days trying to win a race they never chose to run. They long for freedom, yet choose paths that chain them. The pursuit of status, applause, validation. And the worst part? They believe they're evolving, when in truth, they're only moving further away from themselves. Let me tell you something few have the courage to face. Success without understanding is just another form of failure. Because if you don't understand what you're doing, success becomes an accident. And accidents don't set you free. They enslave you. When you act only for the result becomes your master. But when you act for the love of understanding, you are in control, and life begins to flow again. There is no purer pleasure than the pleasure of truly understanding. When you truly understand, there's no need to compete. There's no envy, no rush, no comparison. There's only a curious silence, that rare moment when everything makes sense for just a few seconds, and you feel part of something far greater than ambition itself. The problem is most people want to understand the world, but they don't want to understand themselves. They crave answers but can't stand questions. And that's why they live tired, anxious, and empty. Because they try to fill what is spiritual with what is material. They try to buy, conquer, or prove what can only be understood. Life is not a podium. It's a laboratory. You're not here to win. You're here to discover. And when you understand that, you realize the whole game changes. It stops being a competition and becomes an investigation. Every mistake becomes a clue. Every failure, a new hypothesis. And that's how you begin to free yourself. Not by winning, but by understanding. When a human being finally lets go of the need for recognition, something extraordinary happens. They are reborn. The mind becomes light. The heart becomes quiet. And for the first time, they begin to taste real freedom. Suddenly, fear disappears. The fear of failing, of being judged, of not being enough. Because now, none of that matters. You no longer live to prove. You live to experience. And in that moment, life starts to align with who you truly are. Opportunities appear. Ideas flow. The right people come closer. Because you stopped being a copy begging for acceptance and become an authentic source of energy and creation. Authenticity has a power the modern world has forgotten. When you are real, the entire universe seems to recognize you in a way applause never could. Life begins to conspire in your favor, because at last you're playing the right game, the game of growing from within. And everything that once seemed difficult begins to happen naturally, because when your focus shifts from appearing to understanding, you connect to the natural flow of things. You don't force, you simply are. Do you want to know what true peace feels like? It's waking up one day and realizing you don't need to impress anyone, that you are enough simply for being here, learning, failing, trying to understand. And from that moment on, every gesture, every word, every small discovery starts to have meaning. You begin to see beauty where you once saw routine. You begin to see purpose where you once saw haste. Likeness is born when vanity dies. And the pleasure of discovery becomes greater than any achievement. Life flows, not because you control it, but because you understand it. And once you understand, you no longer need to run. You realize that what truly matters is not what others think of you, but what the universe reveals when you finally choose to listen. Now write this in the comments. With conviction, I choose the freedom of understanding. This phrase will begin to reprogram your subconscious, reminding your mind every day of what truly matters. From today on, make yourself a promise. Live for the love of understanding, not for ambition. Stop chasing recognition and start seeking meaning. That is the key that changes everything. If this message touched you, like the video, subscribe to the channel, and turn on the bell because what's coming next will expand your mind even more. And remember, to understand is to be free, and the one who becomes free inspires the world, without needing to say a single word.